صباح الخير. أبدأ بالترحيب بالجميع من محاضرين ومشاركين باحثين وطلاب. هذا اللقاء محبب على قلوبنا كونه يجمعنا بطلابنا الأعزاء الذين نرى فيهم مستقبل هذا البلد ونعلق آمالنا عليهم للاستمرار والسعي للأفضل رغم الظروف الصعبة. عندما طرح بروفيسور جهاد توما علي فكرة هذا المؤتمر تحمست كثيرا للمشاركة في التنظيم لإيماني بهذا النوع من العمل الذي يستهدف الجيل الشاب ويحضره للتعاون المستقبلي مع بعضه البعض. أود شكره على انفتاحه وتعاونه المنتج والمثمر في كافة مراحل التحضير. الشكر موصول لزملائي في اللجنة المنظمة الأساتذة أيمن كشمر جيسيبي دي لا سالا وتوفيق الأرودي، بالإضافة إلى طالبة الدكتوراه مريم الأخضر على مساعدتهم ومساهمتهم الفعالة على كافة المستويات. أخص بالشكر السيدة هبة حمود على مهنيتها وتفانيها ومساعدتها في كل تفصيل. نبقى الآن مع كلمة البروفيسور جهاد توما مدير مركز علوم الرياضيات المتقدمة الكامس. بروفيسور توما، المنبر لك.
شكرا عزيزتي فدا. أنا كثير انبسطت بالشغل معك، تعرفت عليك أكثر وعندي كل التقدير لمهنيتك ولتفانيك من موقعك كأستاذة وكمديرة وكمربية. I will now switch to English where I'm more comfortable in trying to give you an idea of how the meeting came together and prepare for this morning's session. I'll try to be very brief. So I'm the director for the Center for Advanced Mathematical Sciences at the UB and a professor and chair in the Department of Physics. And in the context of all the crises that are befalling us, whether local or global, it was natural to think of reaching out to the network of our students, graduates of math, computer science and engineering departments in Lebanon, and to try to connect with them with the availability and increased use of online technology to get a sense of the work that they are doing and try to give an inspiration for the young and upcoming students here in Lebanon, as well as strengthen the network of professional network around the research in mathematics in Lebanon and in the community of students that have achieved their first degrees at universities in Lebanon. With that in mind, the idea came together to put together this meeting, and the excitement was immediate, whether from colleagues in math departments and around Lebanon, or from the students whom we ultimately contacted. And judging by the reaction to the meeting as it came together, the excitement is shared not only among the organizers and the participants, but also around a wider audience of colleagues who feel both inspired and are very much looking forward to the development of this meeting with a view to extending it and replicating it in other contexts. So the meeting is structured along thematic sessions. Our organizers have tried their best to organize the contributed talks along themes, okay? It makes for a diversity of talks, essentially 15 minutes talks with invited lectures, which are on the order of 20 minutes long. Okay, we further have invited two colleagues, fresh graduates essentially, for what we're calling invited perspectives. They're perspectives of professional nature of colleagues who graduated and are basically considering work opportunities in mathematics this morning by Fatima Mrouwe, and in theoretical computer science tomorrow in a session dedicated to the subject by Badi'a Ghazi. These are very exciting talks for us. They're of a mentoring nature, offering prospects for work in academia on one hand and industry on the other. Another very important segment for us and an essential item for me personally, and I know it is the same for my fellow colleagues in the organizing committee, is trying to explore the issues faced by women who are considering career path in mathematics. And with that in mind, we have invited Professor Barbara Nelli to give us a broad public lecture on the subject, leading to a discussion. And I want to make sure that you all attend and invite others to attend the session, which will be held tomorrow at 1 p.m. So it will be a 20-minute presentation by Professor Nelli, followed by a wide-ranging discussion. And you will be hearing more from Professor Fidel Shemi via email later on today. So for this morning's sessions, we have the invited perspective by Fatima Mroui, which will be followed by presentation by Wael Farah, Cynthia Atiyah, and Rena Dannawi. Fatima will speak for 25 minutes with time left for questions. And then we will move on to Wael, who will speak for 15 minutes and so forth. Fatima, let me just introduce you briefly. So Fatima is a graduate of the American University at Beirut, and she went on to pursue a PhD in a co-tutelle mode with colleagues at Bordeaux. And she's now a full-time lecturer in the math department at AUB. I am particularly excited to be kicking off the meeting with Fatima's lecture, in many ways giving us a perspective on what's it like to be passionate about mathematics, be a woman and pursuing a career in mathematics, the challenges, the excitements, the limitations, and the visions for ways forward. Fatima, thank you very much for taking on the challenge, and I'm very much looking forward to your talk.
Thank you for the introduction, and good morning, everyone. Thank you also for the organizers for this nice invitation. Based on your request, we're shedding light this morning on the difficulties that women in mathematics face in Lebanon when trying to carve a path in academia. So this is the first part of my talk. Well, let's start by looking at some numbers. Looking first at the professorial versus non-professorial distribution of faculty by gender in the math department at AUB, we clearly see that as we are going up the career ladder, the proportion of women decreases significantly. So here note the number of instructors that are females, and instructors are teachers holding a master's degree, lecturers hold a PhD degree, but their position is just in teaching, is restricted to teaching, and we have the professorial rank faculty members whose position involves both teaching and research. And note that there are no full professor female members in the math department at AUB. Also looking at another distribution for the professorial versus non-professorial faculty members in the math department at the Lebanese University in Hadat branch, we also see that as, again, we are going up the career ladder, the women simply disappear. So probably one may say that this is due to women are not interested in mathematics, for example, or they are not seeking higher studies in mathematics. But simply by looking at the contributions in this conference, we see that we have 24 contributions by women versus 11 contributions by men. So this means that in the Lebanese context, women are pursuing higher studies in mathematics, yet they seem to be less likely to be represented in the professorial rank. One reason may be due to the fact that women's share in the workforce in Lebanon is simply 23%. Just to have an idea of what's going on in other places in the world, let's look at the distribution of or the percentage of women as we are going up from bachelor degree in mathematics to PhD to senior faculty in different prestigious universities in the States. So in this case, we clearly see that the low percentage of women in mathematics in senior faculty position reflects kind of the pipeline of the previous years of bachelor and PhD degrees. So I think that the situation in this case is not the same as in the Lebanese context. And in addition, in the States, for example, women constitute 46% of the workforce, yet they only comprise 25% of computer and mathematical occupations. So I think that the situation is not similar between the two countries with respect to interest of women in mathematics. Well, in general, this is actually this area is an active area of research for people in business and human resources. And a study by Emmanuel Latour in 2008 showed that the evaporation of women at every step of university career is an international phenomenon. It's not just a local phenomenon. Now, let's look more at the Lebanese context and try to kind of decipher what are the main causes for this underrepresentation of women at higher university levels. Let's start in general from the Lebanese context. You all know that we are in a turbulent geopolitical situation with a country poor in resources, collapsing economy, repeated blockage of the government, and all of these are factors that lead to very low employment levels, so underemployment. And in addition, on top of these, all of these factors, we had a Beirut blast in 2020, which also affected a lot the academic sector. And more importantly, last year, particularly for women, we had COVID-19 and lockdown that added the burden on women because they had also particularly for mothers, because also they had the responsibility of homeschooling their kids who never went to school last year and most of this year. So this is the general context that we are in. And before all of these, the Beirut blast and the COVID-19, we already had studies by colleagues Fida Afyouni and Charlotte Karam published in 2020 that showed that Lebanon is distinguished in the region as one of the countries where career path for women are the worst in the region. And in 2018 particularly, it turned out that men have 90% more chance to obtain senior positions than women in Lebanon. Now let's try also to take a closer look in order to understand what is the situation for women particularly. Well, the main obstacles that may be a source of this discrepancy for women is that the society's simply expectation that states that a female is first a wife, a mother, and then a career woman. Another thing is that women are stereotyped as emotional and as being geographically restricted, meaning that they cannot travel in order to attend a conference or a workshop and leave their families behind. And as a result of this picture of women as the primary caregivers also at home, balancing demands of work and family becomes a challenge for working women in Lebanon. And these responsibilities are not really complete obstructions to their career progression. Rather, they slow down the pace and they limit the time they have to produce research. So if you want to be seriously engaged in research as a woman, you have to put in a lot more effort than men. Also, due to the familial demands, women can be deprived in many instances from access to training, professional development, which is also considered as a lack of resource. And as a result, female academicians will publish fewer research studies than their male counterparts, which also affects promotion because in this case, research is an important criterion. Another obstacle in Lebanon is the scarcity or absence of research positions. And I think that this affects women more than men, because when in a teaching position, since women must also devote time for their families, they will no longer have time for research, while men holding similar positions do have enough time for research. Now, on the other hand, there are some factors that facilitate women's attainment of senior positions in academia, such as familial support, where familial support turns out to be an important factor in motivating and encouraging women to pursue their higher studies and also to get to senior positions. Personal traits such as confidence, determination, and self-reliance, these do help women a lot in their ascension in higher education, in addition to the support from the mentor or the advisor or a certain role model. So the natural question then would be, what can be done to improve the climate of university mathematics department and to eliminate this gender gap in mathematics? Some brainstorming or recommendations may be that mathematics department could extend more offers to female mathematicians and can be actively trying to recruit them. Also, they may invite female mathematicians to speak at least once a semester, and this will serve, these 2 points will serve as providing a female role model to mathematics students and help in negating the stereotypes existing about who can be a mathematician. Another point would be developing a sustainable virtual and physical platform that can expose, motivate, and empower many female junior researchers. And this platform may help in training also on particular skills like producing competitive research proposals that can meet international standards. Also, due to the financial situation here in Lebanon, institutions may try to collaborate with international organizations that are willing to support women in science and mathematics, and such collaborations may help women, many women, fulfill their aspirations as researchers. More importantly, at the individual level, I think that women must start with themselves and try to change their mindset and determine what they want as individual. In general, whether it's a woman or a man who wants a career, they should work hard, be optimistic, and have a positive attitude. And as the saying goes, success is built on failure. Indeed, in my case, I also was an instructor at the mathematics department at AUB, and I had 3 kids. 2 of them were toddlers when I decided to continue with a PhD in mathematics in Côte between the Lebanese University and l'École Centrale de Nantes, in addition to 1 supervisor from University of Bordeaux. This was not a simple decision. I had to leave my kids for several months in a stretch sometimes. Again, several factors have helped me in this case: familial support, my own determination to continue my study, and more importantly was my advisors who admitted to start with a student in such a situation. So I think this was a big move that I made in my life. I think it was worth it. And the lesson that I learned from this decision is, if you want to do something, go for it, don't hesitate, but try to think twice before you decide. Well, in the remaining time, I will introduce some aspects of the research that I got involved in this journey. basically, which was about applied mathematics with emphasis on cardiac electromechanics. So just to give you a rough idea of what the topic is, you all know that the heart is the muscular organ that contracts to pump blood to the whole body. And this contraction is initiated by the generation and propagation of an electrical signal, which is called the action potential. Now, simulations of cardiac electrical activity are important in understanding cardiac arrhythmias because sometimes in vivo experimentation is impossible. Such simulations require accurate and stable realistic models to start with, and accurate and stable numerical methods. It's also important to note that there are several scales. It's a macro scale problem. We have the macroscopic scale, for example, in which we look at the propagation of the wave at the level of the organ. And there is the micro scale that describes the source of this electrical activation at the level of the cells. Well, the cardiac tissue is mainly constructed from cells, the cardiomyocytes that consist of an intracellular space separated from the extracellular space by the plasma membrane. And this plasma membrane contains some channels through which ions can flow from one side to another, creating a change in the transmembrane potential. So the sequence of events starting from the activation point back to the resting state is the electrical signal, which is called action potential. Now, in our research, we were interested in several aspects of cardiac electromechanics. The first one was deriving a macroscopic model for cardiac electrophysiology from a microscopic model by asymptotic analysis and homogenization. A second approach was proving the existence of a weak solution for a partially linearized cardiac electromechanical model. A third one was proposing a control volume finite element scheme for the monodomain model used in cardiac electrophysiology and the numerical analysis and simulation of the scheme. And in addition, last year, I was involved in proposing some kind of discrete and continuous stochastic models for the spread of COVID-19 in Lebanon. For sure, I will not go over all of these topics. I will just select the third point, which is about the numerical analysis of a positive CVFE scheme to talk a bit about it. So what is the monodomain model? The monodomain model consists of a reaction diffusion equation coupled to a system of ODEs where V is the transmembrane potential. The vector W represents the gating variables, which represents the opening and closing of the channels in the membrane, with C being the concentration of calcium and lambda is the conductivity tensor, with initial conditions and a Neumann boundary condition, a homogeneous Neumann boundary condition representing an isolated tissue. Well, there are several works on the convergence analysis of finite volume schemes for such models, but with simplified ionic models. In our case, we proposed a scheme for a realistic physiological model that guarantees the maximum principle under the anisotropy condition, following the ideas of Kansas-Guichard on the flow in porous media and Kansas-Brahim Saad in a chemotaxis model. Well, to start with, we had to define a weak solution for this model, which is given by functions V, W, and C in those spaces, verifying this set of equations. We can easily prove the existence and uniqueness of such a weak solution. And in addition, one can theoretically prove that whenever the initial condition verify those bounds, also the weak solution is supposed to verify the same bounds. Now, going to the numerical simulations, the first idea was to use a finite element approach for the simulation of the monodomain model with an anisotropic tensor. So we used for the finite element method FreeFAM++. We conducted the simulation on a rectangular domain for academic reasons. And can you see the movie? So starting with the stimulus from the left side of the domain, we had a wave that propagates in this rectangular domain. And we clearly see the oscillations that appear in the wave front and similarly at the bottom. So I hope that you were able to see the movie. Now, recording at one point of this domain, the action potential, we clearly saw that there is a drop in the value of the transmembrane potential way below the physiological value of -85 millivolt, which means that in this case, there is a clear violation of the maximum principle. So the idea was to resort to a combined finite element, finite volume approach, which is the classical CVFE scheme. We're starting from a primal triangulation of the domain. We construct control volumes around every vertex. And we use, in this case, the stiffness coefficients as in the finite element method. As a result, we had this discretization. So we used semi-implicit in time Euler discretization with the diffusion term discretized as follows, making use of the finite element approximation. And as a result, so we implemented again this scheme using Matlab. So we see here the primal triangulation in blue, the dual control volumes in green. And again, running the simulation on the same domain. So we clearly see that starting with the simulus at the left side of the domain, how the wave, the electrical wave is propagating with almost no oscillation seen. Sorry. And when we recorded again at the same point as for the finite element method, the action potential with this scheme, we also saw that there is a drop in the value of the transmembrane potential below the physiological value. So the idea was to look more closely at the diffusion term in the equation. And we realized that the discrete maximum principle can be obtained with the scheme, provided that the stiffness coefficients are all positive. So as a result, we wanted to modify the diffusion term because the condition lambda KL positive is not guaranteed with an anisotropic conductivity matrix. So since we don't want to modify the lambda KL, we modified the second factor by using a simple idea obtained from the mean value theorem. So we replaced x minus y by eta into px minus py with an appropriate choice of the functions eta and p. And then with the upwind scheme, we modified this equation to get this equation, which is now what we call the positive CVFE scheme or the monotone CVFE scheme. Now, we established also that with this scheme, there exists a solution of the scheme that converges along a subsequence to the weak solution. And also the solution verifies the maximum principle. And validating this with the numerical simulation, we clearly see now that there are no oscillations in the wave. And similarly, the maximum principle is verified. So there is no drop in the value of the transmembrane potential below the physical value. Similarly, when we recorded the action potential, we clearly saw that the action potential is just the usual one with no oscillations in it. We also tried to run a simulation on domain mimicking the a cross-section of the heart with the right and left ventricles. And we recorded also the action potential at points A, B, C, and D and E, starting with a stimulus very close to point A in this region. And also we realized that in this case, the maximum principle also was verified with the simulation. Now, for the physical or the biological validity of the model, we also computed the conduction velocity, the speed at which the wavefront is moving for the different schemes. And it turned out that with the positive CVFE scheme, the value was the closest. So the 57 plus or minus 5 as a standard deviation was the closest to the physical range of values. So this was the advantage of using this positive or monotone CVFE scheme. Now, from another point of view, the positive CVFE scheme showed a slower rate of convergence. So the next step would be to improve this scheme to avoid numerical diffusion and to use it in simulations of cardiac electromechanics, not just in electrophysiology. Another perspective of our work is to mathematically analyze fully nonlinear electromechanical models with different constitutive laws. A work in progress is the microscopic modeling of cardiac electromechanical activity and its subsequent homogenization. I think my time is over. Thank you for your attention.
Thank you very much, dear Fatima, for first
Welcome.
taking on the challenge of introducing or kicking off our meeting with an overview of challenges facing women, ambitious women in the mathematical sciences in Lebanon. It was an amazing job from my perspective. And then moving on to give us a sense of your very exciting research in mathematical biology. We have a couple of minutes for questions. Any questions from the audience? There is always room for you to pose your question through chat, and we try to pick it up around a break, take a few minutes to handle those. I understand it is a meeting with multi-layered, multi-dimensional talks. So you're not always prepared to respond immediately. If there are no questions, I'll ask you a couple of questions. Yes?
There's a couple of hands raised if you.
Okay. I did not see that. Please proceed.
Hi, Fatima, and
Hi.
thank you for this talk. I just have a comment to make about the first part of your talk. Mainly, whenever there's a minority, you see they try to unionize. This is what usually happens. Unfortunately, I haven't seen this much, at least on campus, in the STEM field, like in mathematics, whether between students, like the student chapter have a role, first of all, to unionize and to lobby somehow. And also the instructors and the professor has a role to also lobby and encourage this lobbying among students, whether by, and also the funding institutions, since we're here at the conference funded by CAMPS, has also a role to also support this kind of lobbying in order to encourage, well, let's say, women in mathematics. If there's not enough women in mathematics at AUB, let's say women in science or women in STEMs, I'm sure there's a big number that can be, that can lobby and that can create some,
women have started requesting institutional support, I think, from what AUB has for women already as packages of support, like for maternity leave or switching the clock for them. But other institutions do not have such packages of support, I think. So this is one point. Yes, I don't think that there are any kind of lobby or union between women in mathematics from any place or in Lebanon or even in STEM fields. There isn't anything as such up to my knowledge, but we have several studies so far, mainly conducted by colleagues at AUB, Fida Afyouni and Charlotte Karam, about such issues, in addition to Dima Jamali, when I reviewed the literature about the topic. So we only have studies, we don't have any union or any...
some collaboration even with associations.
Any collaboration.
outside Lebanon?
Exactly.
Because there are grants that are especially for women in mathematics.
Yes, there are grants like L'Oreal UNESCO for women. That's what I know about. Anything else? I'm not sure.
Thank you, Ahmed, for a very important question and remarks. Ayman, you had your hand raised. Did you want to ask a question?
So probably time is up, but it's a short question. So Fatima, probably you mentioned this, but why you check every time if the maximum principal is satisfied? Is it about a check of convergence of your scheme?
No, it's actually for it to have a biological meaning, it must verify what's going on in reality inside our cells. So if I have a value that does not verify this range of realistic values, then this means it's not realistic.
Okay.
That's one reason. Another reason is whenever you want to couple this with mechanics, this will also pose a problem for the way how the heart will contract in your simulation.
Mm-hmm. Okay, thank you. So maybe we'll discuss further afterwards. Thank you.
I also have many questions for you, Fatima, partly science and partly on the work in mathematics and the role of CAMS in that direction. We've discussed it briefly, and I hope to pick it up with you further during the summer. Much to discuss. Thank you very much.
Thank you
for your beautiful lecture. Okay.
Thank you.
We now move on to Wael Farah. Wael graduated from NDU and went on for a PhD in astronomy at Swinburne University of Technology in Melbourne, Australia. I think, if I'm not mistaken, Wael, you had your first taste of machine learning and astronomy at NDU, but you can correct me on that. And then he went on to do work applying fairly sophisticated machine learning technique in an extremely lively field of time domain astronomy, and particularly in relationship to the search of impulsive radio sources. So Wael, very much looking forward to your talk.
Thank you, Jihad. And yes, I can confirm I did a bit of machine learning during my master's at NDU. Okay, let me just share my screen. Can everyone see my screen?
Yeah.
Perfect. Okay. Just for starters, I might be the least qualified mathematician here on the call. So my background is in astronomy, but I did, of course, did a lot of applied math and statistics during my PhD and now during my postdoc. So I'll be talking mostly about my work that I've done during my PhD, as Jihad has mentioned. Yeah, so let's start. So I'll be talking about fast radio bursts. So this is what I've done during my PhD. Fast radio bursts, or FRBs in short, they are the new hot topic, I would say, in modern radio astronomy. They are super bright and super narrow bursts of radio emission that appear to be coming from outside our galaxy. And when I say outside our galaxy, I mean halfway through the universe. And they have unknown origin. We still do not know what generates them, how they are generated. All that we know is that they are super bright, super energetic, and they can repeat sometimes. So it's an extremely dynamic field. And they are really important astrophysical probes because they come from so far away and they are impulsive. They carry the imprint of the intergalactic and the interstellar media as they propagate through that media towards the Earth. And so just to describe what a fast radio burst would look like in our data, this is a plot describing the very first fast radio burst that was ever discovered. And it's coined the Lorimer burst after the person who discovered it. Here, so on the y-axis, we have frequency. This is the frequency of light. And in the radio, we look at light at the gigahertz frequencies. And time is on the x-axis. And so you can imagine here our radio telescopes are taking a spectrum of the sky for every half a millisecond or something. And this, every spectrum here will be a single column in this plot. And so if a fast radio burst would look something like this, it's a dispersed signal. So at higher frequencies, the radiation would arrive first compared to the lower frequency. And now if you sum everything in frequency, you end up with this small peak here. I'm assuming people can see my cursor. I hope people can. This dispersion comes from the fact that radio emission, as they travel through ionized plasma, they interact with the ionized plasma in a frequency-dependent manner, such that they end up in this fashion. So I'm not going to go into details in that, just because radio emission, which is a broadband that is a single line, I would say here, or a single spectrum, traverses through the interstellar medium and the intergalactic medium and propagates through electrons. They get dispersed. And so my talk here will be mainly focused on the detection of these things, because one, they are super important and they're super, super new, and the challenges in detecting these things. And so FRBs are so common in the universe, but are so rare to find because we have very limited telescope field of view, as I will describe in a minute. And we have a lot of human-made sources of interference. So anything that transmits in the radio gets picked up by radio telescopes, and they pollute literally our data. So searching for FRBs, I'll talk about the instrument that I mainly focused on during my PhD, which is the Molonglo Observatory, or the Molonglo Radio Telescope, which is located really close to Canberra in Australia. This is me here for reference. So this is Molonglo. It is a 1.4 kilometer array. It has a 4-degree field of view. And so here you can see the field of view of the instrument. And just one second. Yep, you can see the telescope field of view. And the way we search for FRBs is we just tile the entire field of view with 352 eyes on the sky. So every single banana-shaped green, oval-shaped thing here is a single beam on the sky that gets processed independently in an independent signal path to search for FRBs. And so we end up with something like 22 gigabytes per second throughput. So we need to process everything in a real-time fashion, because we cannot save 22 gigabytes per second. That's practically impossible. And we have to make decisions on the spot whether we find an FRB or not. And so how do we search for an FRB? A de-dispersion algorithm. So if we need to remove the dispersion of the dispersed signal, this is an extremely parallel algorithm. And so we can use graphical processing units to do that. And so this search is applied in dispersion measure. So the dispersion measure tells us how much dispersed the signal is, the width in time, how wide the signal is, and where it appears in our data. And so an example of how a brute force dispersion algorithm or de-dispersion algorithm works is that we test for multiple dispersion measures. We find the best dispersion measure in some weird unit of parsec per centimeter cubed. Let's not talk about this for a second. And then we shift in frequency to get a de-dispersed signal. And then we sum in frequency to obtain a time series. And then we search in width to find the best width for the candidate. And so at the end, we end up with a candidate that appears in a fan beam, in one of those eyes on the sky at a particular time sample, particular signal to noise, dispersion measure, and width. And so all of this can be run in real time. So we already solved this problem. But the issue is, when we're on sky and trying to search for FRBs, we end up with so many candidates, and everything gets sort of polluted because there's a lot of interference in our night sky, in our radio night sky. And so this is a plot that just shows how many candidates we end up with on a daily basis. And so here on the y-axis, we've got time, on the x-axis, we've got beam, and everything that we see here is just a bunch of candidates. So here we've got around 500 500,000 candidates per day. If we're really a bit clever about how we select our candidates, we can end up with around 50K candidates a day after some sort of a thresholding. We can also be a bit more, also a bit more clever into how we select our candidates, we're still going to end up with 1,000 candidates a day, which is kind of a lot. And it's kind of messy. So we do not really want to deal with all of this. And so, you know, this particular plot, I show that, you know, there's an FRB in there, but, you know, a human cannot easily detect this FRB. And so we need something more sophisticated. We need an automation. So what really generates those false positives? Anything really, from a microwave oven to a satellite in the sky to electric charges from lightning storms. You know, everything can really generate these candidates. And so there's no way we can remove them easily from our data. So we have to live with them. And so why do we really need real-time analysis? Well, a few things here. First of all, we have less human intervention. So we don't have to, you know, pay for someone to just look at the data 24/7, and it's a human intensive task. We can also trigger other telescopes if we find one in real time because they are super rare, and we can also save the native data resolution of the instrument. Right? Remember, we have 22 gigabytes per second. If we manage to find one in seconds when the data is being recorded, we can actually manage to write the data down to disk. And so during my PhD, I built this pipeline. I'm not going to go into details here. It's a Python/C pipeline where I run this GPU-based code, and then I generate a bunch of candidates, and then it goes and feeds into a random forest classifier that makes a decision within 20 seconds from when the electromagnetic wave strikes the instrument till when we make a decision. And so random forests are supervised machine learning algorithms. When I say supervised, means that the algorithm was trained on a training set that already contained radio frequency interference and already contained pulses that really look like FRBs but are not really FRBs. And then this was trained and deployed in real time to detect and select candidates that are real. Some of the features that I've used in this algorithm are the signal to noise without any dispersion correction. I also selected, because the major number of candidates that come from our at our instrument at least are phone calls, and so some of the features are sort of tuned towards detecting how much power there is in certain frequency bands that are known to have phone call activity in them, and some other statistical numbers. Yeah, here I show also that there's a pulsar pulse within a phone call at the same time, and the algorithm managed to detect it. And so results. So the best results I would say during my PhD is that I discovered this FRB 170827. That's just a phone number that we give those FRBs. But essentially, we found it in real time. So the algorithm found it in real time. And we actually managed to save the real-time data product to, and it looks something like this. And so, you know, we came from a single peak here in time. So this is time here. Because we managed to save the real-time or the high resolution data of our instrument, the FRB didn't look, well, we resolved the FRB essentially. And we ended up with a profile that looks something like this. We have peaks that are separated by microseconds. So you can imagine a process in our universe that that is so energetic, and it happens on a microsecond scale. This is something that's still, you know, it's a big sort of question mark in the field. What can actually produce something like this, like that much energetic, and can be separated by only microseconds? And so yeah, so that was basically the one of the biggest results that I got out of this pipeline. And thank you.
Thank you, Wael. Perfect time, and we have time for questions as a result for that. Any questions from the audience?
Okay, I have a simple question, please.
Please, go ahead.
First of all, I want to thank you for your talk. It's really interesting. I'm not specialized in astronomy, but to get the point, so you have been trying to measure the FRBs. So your process or your study was to measure this or to detect the FRBs. Okay, is there any study or any plan or some inverse problem to detect the origin of the FRBs? Have you tried some algorithms, a backward algorithm or an inverse algorithm to just detect what was the origin or at what time it was initiated, maybe?
Yeah, that's a good question. That can be sort of expanded a lot, but in radio astronomy, we have a few tools in our disposal to allow us to do something like this. And one of them is using interferometers to try and find from where the FRB is coming from in its host galaxy, right? So we can take an image of the sky and we can know exactly from where the FRB is coming from. So we have that information, but we do not have more than spatial information, I would say. So we know roughly from where it's coming from in its host galaxy, but we do not know exactly what generates it. So that's the big mystery.
Thank you.
Okay, we can take a question from.
I have a question, Jihad.
Marwan, yes, please.
Yes.
Sure.
Okay. Thank you, Wael, for this interesting presentation. Well, I have a question regarding the training part of your algorithm. You said that you do the training or the learning on the fly. I mean, when you are observing, you do the learning part. But what kind of data do you use for learning? I mean, to detect the FRBs, how many detections do you have first? And because you said you do it with the random forest algorithm. And second, what is the type of the data in terms of size and the content? Thank you.
Yes, good question. I'll make sure I'll be fast here. So the training set is divided into two sets: a set of interference signals that we know that have been pre-classified as interference. The other set, or the other class, is a bunch of single pulses that come from pulsars. Pulsars are stars or dead stars that FRB sort of look like them. And so this is my division. We have roughly, I think, 10,000 by 10,000 classes for each. We cannot use FRBs to do that. We cannot use FRBs as a single class on their own because FRBs are super rare. And we've only known, or at least the Molonglo radio telescope has only detected maybe 10 of them. So we do not have enough data as FRBs to do this. So we sort of lie to the algorithm, making it think that pulsars are FRBs. And the data that is being fed to the algorithm is not the frequency time matrix, but a set of features that are extracted from the frequency time matrix. And here I list some of them. And those are what actually get fed into the algorithm for it to perform the training.
So could you be detecting a pulsar instead of an FRB?
Yes, but pulsars can be sort of distinguished from FRBs with many other things, including dispersion measure and their location on the sky.
Okay, thank you, Wael.
Thank you, Marwan. Raidan Al-Aridi had a hand raised. Did you want to ask a question?
Yes, I would like to ask one question. So detecting the FRBs, so do you expect that this energy we could use it, transform it to use it in our daily life?
Use it in our daily life. That's an interesting question. Probably not, at least not in their current form. But there's a lot of I would say applications in astronomy where, for example, pulsars. I've been talking about pulsars. Pulsars can be actually used to as like a GPS sort of so to know where you are, on Earth. You can actually point at pulsars if you have radio instruments, and you can actually pinpoint your location on Earth using pulsars. And so I do not have a direct answer to this question now, but if you ask me this question in 10 years, I might have an application for FRBs once we know more about them. So
okay, we take one last question from Sarah Najm and we move on to the next talk. Sarah?
Yes, thank you, Jihad. Thank you, Wael, for the talk. I just had one question related to this classification scheme. So instead of actually feeding it data from Pulsars, did you explore any of these techniques used for classification of imbalanced data sets other than just like feeding it data from fake data in a sense?
Yes and no. For the simple reason that the algorithm seems to work. So random forest was enough. It was giving us enough, or I would say it was giving us accurate enough classification, so that we didn't have to look outside the box, right? I mean, if it works, we don't have to fix it. That's basically our approach. But having said that, we looked into feeding the algorithm simulated data rather than data from astrophysical data. But that also creates other biases that we cannot easily fix in our data. So yeah.
Thank you.
Thank you, Wael. Very exciting work, particularly that it led to a discovery that doesn't come by very often. That's wonderful. Wishing you the best in your new position and hope to have you with us again for a more extended talk and discussion. Thank you very much.
Thank you. Thank you for hosting me.
Yeah. Okay, so we move on to the next talk in this morning's session, and it's by Atiyah, who is at the Université de Bretagne Sud. Cynthia will talk about numerical time perturbation and resummation methods for nonlinear ODEs and PDEs. Cynthia, if you can give us a brief sense of your educational trajectory up to the PhD, it would be great. And please, the floor is yours.
Yes, now I'm in my third year of PhD at University of South Brittany in France for developing new numerical methods.
Please.
So I will start. So first of all, I would like to thank the organizers of this conference, and it's a pleasure for me to participate in this event. So the subject of my speech today is about numerical time perturbation methods and resummation for nonlinear ODEs and PDEs. So for the outline, first I will start with a short introduction for these methods. Then I will present the application of this method on nonlinear ODEs and PDEs by showing the advantage of these methods on different examples. Finally, I will finish with some conclusions. Classically, in the field of nonlinear mechanics, many time integration schemes are used. For example, Euler schemes, Ronch-Kutta schemes. These methods are based on a temporal discretization of the problem by advancing the model to solve by discrete time steps denoted by delta t. However, many constraints can appear during the resolution. For example, these schemes may be unstable. They can even lead to a destruction in the physical properties of the problem. And also the choice of the discrete time step delta t, sometimes it's complex. Sometimes it's so small, which can increase the number of iteration and the computation time. So we are interested in studying alternative schemes that have the potential to surmount this constraint and overcome the notion of discrete time step delta t. Thus, the proposition to work with time perturbation approaches. So what is a time perturbation method? First, we consider this problem to solve where M, C, and K are scalars or matrices. So the unknown of the problem here is x of t. X are thought as truncated power series using time as a perturbation parameter. So we write x of t is equal to x0 plus x1t plus x2t2 until xn tn. which where n denotes the truncation order. So we calculate the first derivative in the same way, the second derivative, we inject these expansions in the initial problem, and by identifying the terms according to the power of t, we obtain n linear system to solve. So serious terms x0, x1, x2 until xn are obtained by the numerical resolution of those systems. So we obtain x of t. But this solution is only valid on a specific range or domain of validity called 0 Tmax. Cauchelin proposed an explicit expression of Tmax by this formula. So we'll use this formula for Tmax. To reach high value of t, we will do a continuation technique. So what does it mean? We evaluate a new starting point x of 0 at a new time equal to t0 plus this Tmax. And we solve again the problem with the last valid solution. We repeat the same until a final time t. This method is called asymptotic numerical method, and it will be denoted in this presentation by ANM. So ANM allows to obtain solutions that are continuous in time, so no more discrete time steps, and we know very well how to treat convergent series. However, the drawback of this method is that series might be divergent. So what happens, the domain of validity 0 Tmax in this case will be extremely small, and a high number of continuation steps becomes necessary. So how to deal with divergent series? A team in La Rochelle proposed to work with a time-perturbative approach, followed by a resummation algorithm of divergent series called Borel-Padé-Laplace. It has been applied only on simple academic examples. So I will expose Borel-Padé-Laplace denoted by BPL, and it will be used as a time integration scheme in this presentation. So it's around the following 4 steps. The first step is to compute the series terms, as we already said. The second step is to compute the Borel transform of the series terms. Then we do the extension of the Borel transform by an approximation method called Padé. And the last step will be to compute the Laplace transform of this function p to obtain finally the sum of Borel-Padé-Laplace, this one. So numerical examples have shown that very interesting properties are obtained via BPL. However, there is also some drawbacks. We have the apparition of numerical poles, this explosion in the solution. This is an example by using Padé. So another way to overcome the problem of BPL is to use another method or another algorithm to resumming divergent series called inverse factorial series, and we'll use as a time integration scheme in this presentation, where there is no need to use Padé. So I will not present the details for inverse factorial series. I just want to say that we call inverse factorial series the following formula, such that Vn terms are obtained via an algorithm from Xn terms. So after exposing time perturbation method ANM, a resummation method BPL and EFS, these methods are so recent. So our goal is to understand more the behavior of these methods, develop the way of their use on more complex problems, test their relevance and on different examples of nonlinear ODEs and PDEs, and finally we should present a comparative study between this method and the classical one. So I will start with nonlinear ODE. The first example is van der Pol oscillator. This example is just to validate the methods. So what is van der Pol oscillator? It's a dynamic system described by a variable x of t satisfying the following nonlinear differential equation. This coefficient mu is, as a coefficient is said that it's called the coefficient of nonlinearity. So we will apply our method. So first of all, I should note that no analytical solution for this equation. So we don't know the exact solution. So the Ronch-Kutta of first order, the classical scheme, will be our reference solution. So how to do time perturbation method? As we already said, we calculate the series. As already said, we write the unknown of the problem as time power series, we inject. Then according to the power of t, we find the recurrence formula. that permit to obtain serious terms x of n. So once we have x0, x1 until xn, we have x of t. So we do our continuation technique as already said, and now I will present the numerical result. First of all, I will fix the parameter mu equal to 2, the truncation order equal to 15. I will present the solution of BPL. So as can be seen in figure 1 and figure 2, BPL in blue is in a very good agreement with Ronch-Kutta, the reference solution in black. And also we can say that BPL is able to respect the limit cycle as can be seen here in figure 2. However, BPL has sometimes problems that block the complete calculation of the solution. This is an example when, for example, we choose a truncation order equal to 8, we have this problem. So as already said, a way to overcome this problem is to use inverse factorial series here in this color. So as can be seen, no more pole with the inverse factorial series as expected. So in the third figure, we can see that inverse factorial series is also able to respect the limit cycle of the solution. Now, I will consider the same equation, but I will increase the nonlinearity coefficient mu to 1000. And I will run the simulation until a final time equal to 6,000 seconds. So what is the goal of this example is to see how time perturbation methods can deal with large value of the nonlinearity coefficients where some very fast dynamic in the system is expected. So as can be seen in figure 1 and figure 2, even with high value of nonlinearity coefficient, even with a big final time perturbation methods are able to reproduce the dynamic of the system over large time. Now, same good result are obtained if I replace the second member by a forcing term, A cosine omega t, where A is the amplitude and W is the frequency. So I will present the result. So also we can see that same result are obtained by BPL in blue and Ronch-Kutta, the reference solution, in black. So after validating this methods to the simple problem van der Pol oscillator, now I will present another example. I will consider the nonlinear combustion equation with this initial condition. So as already said, we calculate the series terms and we do our continuation technique. For the numerical test, I will run the simulation until a final time equal to 20,000 seconds. So for this example, we know the exact solution. So as conclusion, as we can see the figure, the solution obtained by the solver of Matlab ODE 45 in green give oscillatory motion, while time perturbation method A and M in red is in a very good agreement with the exact solution in black. This figure is a zoom plot of this area here. So from this slide, I can say that time perturbation method can overcome the weakness of or the problem of the classical schemes. So now I will consider another example. It's elastic hardening spring problem. It is well known that this example is a very good, is a great test for evaluating the performance of new time integration schemes. So as already mentioned, we calculate series terms, we do our continuation technique, and now I will present the numerical result. So we have figure 1 and figure 2. Figure 2 is a zoom plot of figure 1. So results, as can be seen in the figure 2, result obtained with the classical schemes, Ronch-Kutta of first order and fourth order in blue and green color here, show the inaccuracy of the solution, while A and M solution in red here is in a very good agreement with the reference solution in black. Okay, I will present another example of nonlinear ODE. It's Lorentz system. It's one of the famous chaotic systems. And here we have the 3 degrees of freedom. We have 3 variable x, y, z. We calculate series terms for the 3 variable x, y, z. Okay, for the numerical test, I will not present a lot of details. Just I want to say that, for example, here, numerical results show the ability of time perturbation method to reproduce the 2 well-positioned attractors. So this good result motivate us to apply time perturbation method also on nonlinear PDE, in particular those solving fluid problems. I will present first of all level set. So what is level set? It's a popular method for interface capture. It represents an interface gamma here, as can be seen in the figure, as the zero contour of a smooth sign distance function phi xt called the level set function. So phi x of t is defined over a domain omega in this way. And the evolution, the interface evolution of this gamma is controlled by solving the following transport equations. So this one is our PDE equation. So for the classical numerical resolution, I used the final difference. And for temporal discretization, I will use the TVD-RK4 scheme. So as already said, we calculate our series terms and we do our continuation technique. So for the numerical result, I will consider a square domain with initial interface, this one, so it's a circle, and with this velocity. So these two figures show the evolution of the interface using the classical classical TVD-RK4 from initial time t equal to 0, it's a circle, until a final time t equal to 3, as can be seen here. So we are interested to see if this recent method, time perturbation method, are able to respect the evolution of the interface. So first of all, I compare the zero contour or the interface obtained by classical TVD-RK4 in black and time perturbation method BPL in red. So as can be seen, no visible difference between the colors. And also I will compare the L2 norm of the level set function obtained by the methods. So no visible difference between these plots. So now we are interested in comparing the number of steps and CPU time obtained by this method to reach a final time of t equal to 10 seconds. So we have table 1, table 2. As can be seen, time perturbation resummation methods ANM, BPL, AFS need much less step as TVD-RK4 and also much less CPU time than the classical TVD-RK4 to reach the same final time. For example, ANM need 1 second of CPU time to reach t equal 10 seconds, while classical TVD-RK4 needs 6 seconds. So also I validate this method to another nonlinear PDE. It's Navier-Stokes equation. It's a popular PDE describing the motion of the fluid. So we calculate series terms. We have velocity and pressure here. So I choose an example where we know the exact solution of Navier-Stokes, and I compare time perturbation method and exact solution of the velocity and also for the pressure. So results are validated also for Navier-Stokes equation. So as conclusions, time perturbation resummation methods have been validated on different examples of nonlinear ODEs and PDEs. These methods are well suited to simulation over long time, permit to overcome the weakness or the constraint of classical schemes, and the CPU time needed by this method is less than that of classical one. So for future work, we will apply this method to real test case and we'll see if we will see advantage or not. So thank you for your attention.
Thank you very much, Cynthia. The talk went a bit over time, so it leaves us time just for one question from the audience. Okay, if you think of questions, please put them in the chat and I try to raise them towards the end of the session, time permitting. Thank you very much.
We have people are raising hands in the chat, in the participant part of the...
Okay, sorry. Nabil? Nabil, would you like to ask your question? You want to unmute?
Yeah, I would like to thank you, Jihad. Thank you.
Please.
I would like to ask a small question to Cynthia.
Yes.
The question is about have you tested have you tested the method for long times? I mean, how far in the time can you go?
Yes, until now
just let me finish with my second question.
Okay.
Now, did you try the method for problems where the behavior is explosive? Let's say when the solution gets to achieve high amplitudes.
Yes.
Did you have something? Did you test the method in these singular cases?
Yes, I already even tried for a stiff problem where there is the explosion of the solution, and also for overlay a long time, I tried Navier-Stokes equation and many different examples. For until now, I tried until 20,000 seconds.
Okay, thank you.
Thank you, Nabil.
Welcome.
Sarah, we have time for a very quick question.
Yeah, it's a really quick one. So thank you, Cynthia. I just had a question related to the comparison with classical solutions, with classical methods. You were just showing how close the solution is visually. Did you have a measure of error estimates rather than a visual comparison?
Yes, I did the calculation of the error, and it was 10⁻14. Between the method, the temporal method, and between classical scheme and time perturbation method, also we have a very, very small error.
Thank you.
Okay, thank you very much, Cynthia. We now move to our last talk in this morning session, and it's going to be by Rena Dannawi at the École Normale Supérieure de Paris. And she will be talking about modeling vesicular exocytosis in neuronal and neuroendocrine cells. Please, Rena, the floor is yours.
Good morning, everyone. I will start sharing my screen first.
Please.
Can you see my screen?
Yeah, please.
Okay, perfect. Good morning, everyone. My name is Rena Dannawi, a first-year PhD student at Pasteur Laboratory at École Normale Supérieure under the supervision of Dr. Alexander Olenik. My PhD is about theoretical characterization of single vesicular events in exocytosis in connection with oxidative stress and inflammation. And I'm really interested to be talking in a conference that is mapping all the mathematicians in Lebanon. My PhD covers the matters of neurodegenerative diseases, vesicular exocytosis, electrochemistry, where I'm currently working on 2 projects simultaneously. My work includes modeling and simulation, and I will shed light on the details in the next slides. Let's begin with some background information about neurodegenerative diseases, which has been a great inspiration and motivation to our current work. Neurodegenerative diseases are a class of diseases characterized by the death of certain brain cells, resulting in a range of pathologies which depend on the impacted brain cell, such as Alzheimer's, which is associated with the loss of memory, and Parkinson's disease, which is a disorder motor control that follows a deficiency of dopamine in the substantia nigra. Unfortunately, 7 to 10 million people worldwide live with Parkinson's disease, and despite the high cost of the medication for the Parkinson's care, the best treatment for such disorders will treat some of the symptoms for a small period of time. Therefore, we have no cure nor prevention for those disorders. So we need to understand some fundamental relationship and how the process goes to determine the underlying mechanisms and better target the suitable medications. Mitochondria are power centers of any cells in our body and crucially involved in the homeostasis of the cell. In neurons, they are also responsible for powering the neurotransmitters loading into the vesicles, their delivery to the presynaptic area, and neurotransmitters release via the exocytosis. Mitochondria malfunction contributes to the formation of reaction oxygen species, where its embedded production together with reactive nitrogen species will take us to the oxidative stress. So an excessive production of reactive oxygen species and disturbance of the antioxidant system can cause us oxidative stress, which causes many diseases. Also, it is thought to be at the origin of some neurodegenerative diseases by affecting the whole cell, in particular by damaging vesicular exocytosis, crucial for neuron functions. So what is vesicular exocytosis? In fact, cells communicate with each other in different ways, and one of the most important ways is through vesicular exocytosis. As we can see here in this figure, it involves the fusion of a vesicle filled with neurotransmitters with the cell membrane through a nanometric fusion pore. In fact, neurotransmitters are stored in advance in the vesicles. Once the calcium channels open inside the neuron, a fusion happens between the vesicle and the cell membrane, which leads to the release of the neurotransmitters. On another hand, here to the right, we can see the regions of the brain where neurotransmitters are mainly produced. Based on the systems which we are currently studying, glutamate and catecholamine neurotransmitters are playing a role in our work. For example, catecholamine includes noradrenaline and dopamine, where dopamine is located in the substantia nigra, and its deficiency is involved in the Parkinson's disease. In other terms, neurotransmitters are chemical messengers created by the cell nerves to transmit some messages, and they exceed 100. And based on their chemical structures, they are generally classified as amino acids and monoamine, among others, that are involved in our work. And for this case, we are considering the glutamate for the amino acids and dopamine for the monoamine. In fact, vesicular exocytosis at the level of single cells can be probed using different strategies, but with our collaborator, we are using electrochemistry. And we are using amperometry specifically for having two major advantages which are hardly achievable by other techniques, which are high temporal resolution and sensitivity, and the quantitative measurements using the Faraday's law that allow us to quantify the number of the released molecules during a single exocytosis event. In this kind of experiment, as we can see here in this figure, an electrode is placed on the inside in the living synapse, or in the close vicinity of the cell membrane, resulting in an immediate oxidation of the released neurotransmitter molecules that are diffused to the surface of the electrode. Therefore, obtained current that characterize individual's exocytosis event, which we call a spike, will allow us to estimate the vesicle's contents as well the dynamics of the release. So to reveal connections of vesicular exocytosis and oxidative stress, and to get the changes in exocytosis at the beginning and progression of a pathology, it is necessary to understand relations between the original of the signal and its measurements, as well as rationalize various characteristics of the spikes. In this context, during the first months of my PhD, I worked in parallel on two problems. The first one is related to the modeling of monitoring of glutamate release with modified electrode. We worked on the modeling of the quantitative monitoring of glutamate release at neuronal varicosities by enzymatic nanoelectrode. But why we chose to monitor the glutamate specifically? It is because glutamate is an abundant neurotransmitter in the central nervous system of mammals. Unfortunately, glutamate is not electrochemically active molecule, so we cannot detect it electrochemically, but by using a properly functionalized electrode, one can monitor it. Our collaborators developed a modified electrode. And in this case, glutamate can be converted enzymatically into hydrogen peroxide, which can be amperometrically detected by its electrochemical oxidation at the platinum surface of the modified electrode. Due to this additional conversion step, an additional time constant is involved in the monitoring process. So to characterize the single vesicular events from raw experimental data, we want to model the whole process. To detect the in this case, we are considering, in fact, two measurements. The first one is to detect the vesicular glutamate exocytotic release. A nanoelectrode was placed on the immediate vicinity of a neuronal varicosity, whereas to quantify the intravesicular glutamate content of individual vesicles, our collaborators used the EVIAC technique, which is intracellular vesicle impact electrochemical cytometry. And the responses were evaluated by placing a nanoelectrode inside the cell but of course, without breaking its integrity, where the cell collapses on the electrode, and this allows us to quantify the content of the cell. By performing those experiments, glutamate will be oxidized onto the surface of the sensor, resulting in an amperometric current. And to model the process, we are considering the fusion of the glutamate outside of the vesicle and in the extracellular space towards the electrode, where it is detected as described above. In our case, we are not considering the thickness of the enzyme layer. So we are taking a limiting case where the thickness of the enzyme layer tends to 0. So in this case, we are considering the process which is occurring only at the surface. And also we are assuming that the conversion of glutamate to hydrogen peroxide is followed by the Michaelis-Menten kinetics, where we will be interested in quantifying the two parameters, Vmax and Km. We are seeking to extract parameters of the Michaelis-Menten law from the amperometric calibration curve, where we used the Line-Weaver-Burk equation to produce it. Note that at the beginning, our system was composed of the nanometric fusion pore and the cylindrical electrode. Also, we note that the diffusion of the flow of the neurotransmitters from the pore towards the cylindrical electrode is described as here. We can see in this picture. So here we can see the flux of the neurotransmitters from the nanometric fusion pore towards the cylindrical electrode. The other project which we are currently working on is concerned about deciphering the features of the individual spikes. In this work, we considered the experimental data obtained with carbon fiber microelectrode at PC12 cells. In amperometric traces, not all spikes, signals from oxidation of the released neurotransmitter molecules are alike, and they can be classified according to their shapes. We considered the most frequent encounter type of the spikes, the single exponential spikes and the double exponential spikes. This means double exponential decay. And these spikes can be distinguished easily by plotting them in semi-log scale. That's why we can see them here described as in log scale. And here we notice that when the vesicle has only a dense core, we have only single exponential decay. But when the vesicle has a dense core together with a halo, we have double exponential decay. And in fact, 1 exponential spikes have already been rationalized previously by the hosting group, while for the 2 exponential spikes, explanation is proposed by the same group, but quantitative theory is still not available. But we have one hypothesis. The interior of a vesicle consists of negatively charged polyelectrolyte chromogranule matrix mixed with monoamine neurotransmitters, protons, and others. And according to Dejan's theory, negatively charged polyelectrolyte should collapse in proportion with the charge of the cations present inside the vesicle. And since monoamine neurotransmitters and protons have partial or unity positive charge dominate inside the vesicle, the polyelectrolyte matrix cannot fully condense, but instead can be existed in a pair necklace structure. The pairs correspond to compacted chromogranule phase, or which we can call a dense core or slow releasing domain, while this strand can be represented in the non-compacted chromogranule phase, or we can say it as halo or fast releasing domain. And here we can see a secretory vesicle structure, where we have here the nexus structure, and here we have the strand. And because of the small entropy, we have the collapse of the full vesicle in small blobs. But if the entropy was high, we will have a collapse in a one core. And our kinetic model was considered like this. But when we are considering the dense core and the halo, we will have to consider the empty sites which are formed. In this case, the kinetic model will be as following. And here we can see that the kinetic model is, we are considering the empty sites where we have the first exponential slope and the second exponential slope. This allowed us to formalize the process by using system of differential equations describing the exchange between the compacted and non-compacted phases, as well as exterior of the cells when neurotransmitters are released. Note that Q fast and Q slow are expected both to decrease with time as the vesicle is emptying all its contents. But we have one problem. The problem is that even with a simple model, the number of unknown parameters is too big, with respect to which we can be extracted from the experimental spikes. So to minimize the number of the unknown parameters, we developed a dimensionless model and currently working on the strategy to extract the governing dimensions parameters from the data. And here, as we can see in this slide, our model consists of some parameters and the function which determines the dynamics of the opening. And for now, we could be able just to quantify the charge and to have an estimation of K-rho deep max and K1, K0 fast, but we are currently working on identifying the other parameters. And here is the dimensionless parameters that we are currently using, and we have a strategy to work on it on the future. So in this case, my future work will include to finalize these two projects for this year, of course, because they are still in the process. And second, using these results, we will be able to use for the analysis of the spikes, where we are currently waiting for the experimental data from our collaborator. And by the modeling and statistical tests, we mean to do some data extraction and comparison, to do traces analysis and comparison, spikes modeling and parameters extraction, spikes parameter comparison, and all this will be depending on the statistical tests which will be performed. Now I will happily introduce the hosting group, which is composed of my thesis supervisor, Dr. Alexander Olednik, Professor Irina Sever, Professor Christian Amatore, and of course, our collaborator, Professor Huang from the University of Wuhan. Thank you very much for your attention.
Rena, thank you very much for a very concise talk on a complex subject. You managed quite well. We have a few minutes for questions. Yes, Fatima, please go ahead.
Thank you, Rena, for the interesting introduction to the topic. Just I have a question. Can we, well, you have a synapse and you have a post-synaptic cell. I'm not sure whether I understood the concept correctly, but we have a post-synaptic cell. Can't we measure the effect of the vesicle exocytosis that's going on by measuring what's going on post the synapse, yani by the electrical effect that is introduced or something like that?
Okay, in fact, for our case, we have a presynaptic neuron and a postsynaptic neuron, okay? And by presynaptic neuron, we have this video which describes the process. So here we have a calcium which enters inside and which will open the gates for the fusion happens between the presynaptic neuron and the member of the core. So in this case, honestly, we are not considering the postsynaptic neuron, because in this case, we are just caring about the fusion that happens between the presynaptic neuron and the vesicle that happens here. So in this case, when we have the fusion that happens between the pore and the membrane, we will get some electrode to quantify the number of the released neurotransmitters, because as we know that we have some neurodegenerative diseases, and for now we don't have a good hypothesis about the reason of these diseases, but one of the reasons might be when the neurotransmitters are released from the presynaptic neuron before they enter to the postsynaptic neuron. So our work will be honestly to work here on this region, on the presynaptic neuron.
Thank you.
Professor, you are muted.
Rena?
Yes.
I'm just curious about your background before you embarked on this project.
In fact, I have studied mathematics during my bachelor, and then during my master, I studied computational and applied mathematics. And then when I moved to the PhD, it was a bit hard for me to shift for the neuroscience and electrochemistry and physical chemistry. But because of having, as you know, when you are having a good background in applied mathematics, you can apply mathematics and everything. And for me, it was very interesting to apply it in neuroscience.
Exactly. I was wondering about all the challenges of dealing with experimentalists on one hand and getting into all the complexities of the chemistry.
It was a bit challenging for me at the first, but when you are passionate about the subject, you will ace all these obstacles.
Well, all the best. If there are no other questions, we will close this morning session. Thank you all for your attention. We'll have a half an hour break, which will take us to 12 p.m., where we pick up with the second session for the day. So make sure to join us and encourage others to do the same. Thank you all.
Sorry for this unexpected technical issue. I will be moderating this session according to what was planned earlier. So let us start directly with Perla Al-Kettani from l'École Normale Supérieure Paris. She will be talking about singular limit of stochastic Alenkane equations with nonlinear diffusion. So Perla, please, can you try to share your screen?
Yeah. Just a second. So is it good?
Thank you. So the floor is yours.
Thank you. So first I would like to thank the organizers for giving me the chance to talk here today. I'm very happy to be here. I am from I work now, I am a postdoc in the Laboratoire de Physique de l'ENS in Paris, and I am working on some mathematical biological model based on cancer stem cells. But what I present now is totally different. So it's about the singular limit of a stochastic Alenkane equation with nonlinear diffusion. This is a joint work with Daniel Hilhorst from the University of Paris-Saclay, Yoon-Jung Kim and Hyunjun Park from Kansas University in Daejeon, South of Korea. So first, I will start by introducing the simple Alenkane equation. As you can see, we have du dt equals Laplacian u, it's a linear diffusion, plus f of u, it's a reaction term, Neumann boundary conditions, and an initial condition at t equals 0 equals to u0. F has exactly 3 zeros, -1, 0, and +1. F prime on plus and -1 is negative, and F prime on 0 is positive. So plus and -1 are stable roots, and 0 is an unstable one. A typical example of this reaction term is f of u equals u minus u3rd. The deterministic Alenkane equation with linear diffusion was first introduced by Allen and Kahn in 1972 to model binary mixture undergoing phase separation. To get an intuition about the generation of the interface, which is the property of the singular limit, I will start by introducing the equation ut equals Laplacian u plus a small parameter in front of the reaction terms, so 1 over epsilon square u minus u3rd. What I will start doing is to change the time. So rescaling time, we have tau equals t over epsilon square. I'm sorry. Tau equals t over epsilon square. So we get that u tau is equal to epsilon square Laplacian u plus u minus u3rd. For t fixed and epsilon, when epsilon goes to 0, so tau goes to infinity, we have that u tau is equal to u minus u3rd. So for the ODE, if I go from the initial condition 0, I will remain on 0. And if I go from any initial condition which is positive, I will converge to +1. And if I go from any condition which is negative, I will converge to -1. In the case of the PDE, I will have the generation of the interface, a steep transition zone, and between two spaces, two zones. The first one, u epsilon equals to 1, and the second, u epsilon equals to -1. Then this interface will start to propagate according to its mean curvature. So we have the equation Vn equals minus n minus 1 kappa. Kappa is the mean curvature. So for the previous work in the deterministic case, the monotony and Chadsman in 1995, proved in the arbitrary space dimension the singular limit of the equation with matched asymptotic expansions. Chin-Fu Chen in 1992 used the comparison principle and super solution, and our work is very similar to the work of Chin-Fu Chen. And Alfaro, Hilhorst, and Matano in 2008 improved the work of Chin-Fu Chen and proved the additional properties, especially that the width of the interface is of order of epsilon. So now what we will have to do is I will introduce the deterministic Alenkine with the nonlinear diffusion equation. So we have the problem P epsilon, ut equal Laplacian phi of u, which is the nonlinear diffusion, plus 1 over epsilon square f of u, Neumann boundary condition, and initial condition at t equals 0 equals to u 0. For the hypothesis of the problem, D is the smooth bounded domain in Rn, F is C2 and has 3 zeros, alpha minus, alpha plus, and alpha. So here we are in a more general case where alpha is between alpha minus and alpha plus, f prime of alpha minus and f prime of alpha plus are negative, and f prime of alpha is positive. Phi is C4 and phi prime is bounded, has a lower bound, a lower positive strictly bound, is bounded below by C phi, which is strictly positive, and the integral from alpha minus to alpha plus of phi prime of S Fs ds is equal to 0. Gamma 0 is a C4 plus mu. Mu is between 0 and 1. U0 is bigger than alpha in D0 plus, and U0 is less than alpha in D0 minus. D0 plus is the region enclosed by gamma 0, and D0 minus is the region enclosed between the boundary of D and gamma 0. U0 is C2. We have a non-degeneracy condition if X belongs to gamma 0. So those pictures are just so to illustrate the difference between the linear diffusion and the nonlinear diffusion. So we have here, when we have the linear diffusion, you can see that the diffusion and the speed are the same in any direction. While if I have the nonlinear diffusion, the diffusion and the speed will depend on the direction. So now, when epsilon goes to 0 in the problem P epsilon, we will have the limit problem. And the limit problem is given by the problem P0, which is Vn equals minus lambda 0 and minus 1 kappa on gamma t. And gamma t at t equals 0 equals to gamma 0. Vn is the normal velocity of gamma t, and kappa is the mean curvature at a point of gamma t. Lambda 0 is equal to this expression, and the potential W is defined by W of u is the integral from u to alpha plus of f of s phi prime of s ds. What we can notice is that if f of u equals u, so when we are in the linear case, we will have that f prime of u equals 1, and then lambda 0 equals 1. So this constant is because of the nonlinear diffusion, while if we are in the linear case, then lambda 0 will simply be equal to 1. Okay, so now I will add one more difficulty. After seeing the nonlinear diffusion, I will add now the stochastic term. So I will be talking about the stochastic Alenkine equation with nonlinear diffusion. So mainly the problem P epsilon, ut equals Laplacian phi of u plus 1 over epsilon square f of u, and the stochastic term 1 over epsilon xi epsilon. Neumann boundary condition and initial condition at t equals 0 equals to u 0. We have the same hypothesis on D, on F, on phi, and on the initial condition u 0. So for the also for the previous work, Funaki in 1999 proved the propagation of the interface in space dimension 2. Weber in 2010 proved in an arbitrary space dimension the propagation of the interface. Alfaro, Antonopoulou, Karali, and Matano in their preprint proved the generation and the propagation of the interface, but in the linear diffusion. So our work would be also in the nonlinear diffusion case. For the construction of the, so I will start by introducing this xi epsilon. So we suppose that there exists a probability space with independent Brownian motion, Wi equal 1 and 2, W of 0 equals 0, and we define the stochastic process, Wt, equals W1t when t is bigger or equal to 0, and W2 minus t when t is negative. So we let rho be a modifier with support -1, 1, and we have that the integral of rho on r equal to 1. Then for a given epsilon, strictly positive, we define the approximate Brownian motion, W epsilon t, as the convolution of W and rho epsilon given by this expression. Then we define the mild noise, xi epsilon, as the derivative of this approximate Brownian motion, which is W epsilon. In particular, for gamma less than 2/3 and epsilon small enough, it turns out that we have that the absolute value of xi epsilon is less or equal than c over epsilon to the power 1/3, and the absolute value of xi, the derivative of xi epsilon is less or equal than c over epsilon. These properties are taken from the article of Weber in 2010. This mild noise, when epsilon goes to 0, converges to the white noise. Now we will start by the theorem that we proved, which is the generation of the interface. So we have the generation time t epsilon given by this expression, mu epsilon, which is f prime of gamma epsilon, and eta 0 defined by this quantity. Let u epsilon be the solution of problem p epsilon and eta be an arbitrary constant, so between 0 and eta 0. Then there exists a positive constant, epsilon 0 and m0, such that if epsilon is between 0 and epsilon 0, for Lx in D, u epsilon at t epsilon is between alpha minus eta, alpha plus eta. If u0 is bigger or equal than a plus m0 epsilon, then u epsilon is bigger or equal than alpha plus minus eta. And if u0 is less or equal than a minus m0 epsilon, then u epsilon at t epsilon is less or equal than alpha minus plus eta. I will give you shortly an idea of the proof. So the Allen-Kahn equation is recast for small times as ut equals Laplacian phi of u plus 1 over epsilon square f epsilon u plus epsilon g epsilon. So g epsilon is xi epsilon minus xi epsilon at t equals 0. And where f epsilon of u is f of u plus epsilon xi epsilon 0. We construct the sub and super solutions as the solution of the initial value problem. So y tau equals f epsilon y plus delta. This perturbation is because of the stochastic term. And the y at tau equals 0 equals to zeta. And then we construct the sub and super solution, w plus and minus epsilon, given by this expression and with pt equals to this quantity. And then using the comparison principle, we prove the generation of the interface. After that, so the limit boundary problem of the stochastic problem will be, so we will have Vn equal minus n minus 1 lambda 0 kappa minus C0 W point on gamma t, and when t equals 0, gamma t equals to gamma 0. Gamma t is the interface at t positive, Vn is the normal velocity on the interface, kappa is the mean curvature, and lambda 0, C0 are positive constants that we can calculate. So now, in order to be able to define sub and super solutions, we will also consider a family of hypersurfaces, gamma t, epsilon plus and minus, which evolves according to the following motion equation. Here, this is the term because of the stochastic term, and then we have that gamma epsilon plus and minus at t equals 0 equals gamma 0 epsilon given by this set. The times t and t epsilon are defined that as the largest time, such that the evolutions defined by these equations are well defined. So now we will consider the sign distance function. So we denote d in the region enclosed by the interfaces gamma t epsilon plus and minus, and dtx, which is d, and we subtract the interior of the domain d int. Then we have d bar epsilon plus and minus as the sign distance to gamma epsilon plus and minus, which is equal to the distance between x and gamma t epsilon plus and minus for x belonging to d int, and minus the distance for x, minus the distance between x and gamma t epsilon plus and minus for x belonging to dt x. And now we will have the propagation result. So there exists an initial condition u0 epsilon such that u epsilon belongs to each, so I will not call them to each interval if x belongs to d, or if d bar is less or equal to minus epsilon c, or if d bar is bigger or equal to epsilon c for some constant t belonging to 0 capital T. The final results join the propagation and the generation of the interface for a time t between t epsilon and t. And I thank you for your attention.
Thank you, Perla. Probably we have time for one question from the audience. One quick question. So, check. I don't see any raised hands. Just a quick question. In slide 13, you had an upper bound on the derivative of xi and xi itself, xi epsilon. Just what does this mean? Does it help by any means in the passage to the limits?
Yeah, exactly. So these are in order to construct the sub and super solutions and to be able to prove the propagation and the generation properties. So we will have to bound these, let us say, this annoying term, which is here. So we will need these bounds in order to have correct sub and super solutions and to use the comparison principle and to be able to prove the results.
Okay, thank you very much, Perla. I still don't see any hands raised. Anyways, thank you so much. We leave the discussion for later if there are any.
Thank you.
So let us move to our next speaker. And I would like to announce that there is a change in schedule for this session. So the talk at 12:40 will be by Eli Aid instead of Nadine Dirani. So now we are with Maria Ghawi. Can you try to share your screen, please? And unmute yourself. I can't hear you. Probably change the settings, the audio settings. Yes, and we can see your screen. So Maria will talk about a Treff's method applied to elliptic equations. She's a PhD student between the Saint Joseph University and Sorbonne University. The floor is yours, Maria.
Thank you. First, I want to thank the organizers and thank you. It's my pleasure to be part of this conference. I'm in my third year of PhD between the Sorbonne University under the direction of Professor Bruno Depré and the St. Joseph University under the direction of Professor Tony Sayah. Today I present to you a new method called the Traps method that will be applied to an elliptic equation. The Traps method is an approximation method for solving linear boundary value problems arising in applied mathematics and engineering sciences. There are many classical numerical methods for solving boundary value problems on general domains. Usually one calls the finite difference method, the finite volume method, or the finite element method. However, it is more admitted that the Traps method must not be forgotten in this panorama for its important advantages. So first who is Traps? Eric Traps is a German mathematician born in Leipzig, Germany on 1888. His academic career began with his doctoral thesis in Strasbourg, in which he solved a mathematical problem of hydromechanics. Then he moved to applied and numerical mathematics, where he was very successful in research in this field. And in 1926, Eric Traps presented a new method called the Traps method on the second International Congress on Applied Mechanics held in Zurich, Switzerland. This method consists to approximate the exact solution through a bilinear combination of trial functions satisfying exactly the governing differential equation. And now the interest on Traps method moved to time domain formulation of generalized wave equations, coining the name of Traps discontinuous Galerkin methods, noted TDG. So here are some advantages of this method. First, for the same high accuracy O of HM, the number of basis functions per cell is in order M, which is asymptotically much less than the quadrature estimate for the finite element and discontinuous Galerkin approximation, which is in order M power 2. Second, the theoretical advantage of our approach is to reinforce the continuity of the traces using a penalization term while preserving the first point. What about the difficulties? The first is that the basis functions are discontinuous. The second difficulty is the way to obtain the continuity of the normal derivative trace. And an important technical difficulty when it comes to apply the method on an elliptic equation minus delta p plus delta p equals 0 for delta positive is that the trial functions are not classical polynomials. So instead of pure polynomials, exponential functions are used to construct the Traps space. It is the reason why additional technical inequalities for such exponential functions are proved in the core of this work. So let's begin. In the first part, I'll start by applying the Traps method on a simple classical problem, which is the Poisson problem. Then I'll introduce its variational formulation and a priori error estimation illustrated by numerical results. And in the second part, I will apply the Traps method to an elliptic problem by introducing two ways of applying it. In the first one, I will approach the normal derivative using one parameter, while in the second one, I will use two parameters, but the order of the convergence will be more effective. And finally, the conclusion and the perspectives will be presented. So let omega be the polygonal domain with a boundary gamma. We consider the following Poisson's problem. Minus delta p equals 0 in omega and p equals p0 on gamma, where p0 is a given function, it's the Dirichlet condition on gamma, and p is a strong solution, it's a strong solution in H2 of omega. After multiplying the equation by the test function and integrating by part, I approach the normal derivative del pk over del nk by the following system. The numerical analysis of the method will show that using this approximation is a way to restore a strong form of the continuity of the approximated solution pH. However, the text function QH are discontinuous from one cell of the mesh to the other. So the normal derivative of the text function has no reason to respect any kind of the continuity principle on the edge. That is why this approximation won't be used for the normal derivative of the test function QH. Our aim in this slide is to find the approximated solution pH in H2 of tau H of the weak formulation of the discontinuous Galerkin problem. Using quadrature formula on the edge, where alpha IL are the weights of the quadrature formula and the CIL are the ghost points, we define a bilinear form ADG and a linear form L as follows. To finally obtain the variational formulation of the discontinuous Galerkin problem. The subscript DG in ADG refers to the fact that the bilinear form comes from a discontinuous Galerkin approach. The enhanced continuity of the unknown pH is enforced by the third and the fourth contributions in the bilinear form ADG. Now, for small or very small values of the parameter D, as it will ultimately be the case in this work, the continuity of the unknown is strongly penalized, and our understanding is that it is a strong asset of the bilinear form form ADG. And in the following, we will introduce a discontinuous formulation associated to the initial problem by using the trace method. So first, we take an infinite dimensional space D of tau H, where the elements verify the initial equation, and Vm of tau H is the finite dimensional space in V of tau H. In this case, the shape functions are polynomials. One takes T as follows, where T is between 1 and m, and I is the pure imaginary number. These functions are harmonic, so they verify the initial equation. Then we define the new bilinear form AT, which is the restriction of ADG in the space V of tau H, where the elements verify the initial equation. So here we have these two terms equal to 0, so AT will be equal to this. To finally obtain the variational formulation of the TDG problem. Next, we are working on the space H2 of tau H, where the corresponding positive form is actually a norm on V of tau H. So as we can see, if the norm is equal to 0, the first term gives us that the 2k is a constant in each element of omega, and the second one gives us that it's the same constant, and the third one gives us that the constant is equal to 0. Then we show the following proposition. In our weak formulation, the bilinear form AT is coercive, and we prove the existence and uniqueness of the solution by proving that it admits a unique solution in a finite dimensional space, Vm of tau H. Then we establish a priori error estimate between the exact and the numerical solution in norm DG. Already defined in the previous slide, by supposing that the Gauss-Legendre quadrature formula has more than m plus 1 point, and for D as follows, we obtain the following inequality where the order is in 2/3 m. To illustrate this work, I'll show you numerical investigations corresponding to the trace problem in dimension 2 by using Matlab software. So here we consider the square omega, where each edge is divided in n segments, and the mesh step is equal to 2 out of n, and D equal to h power 2m out of 3 plus 1, and we took 7 points of loss. So here we'll take sinus x exponential y as the exact solution. The first image represents the comparison between the exact in the left side and the numerical in the right side solution for n equals 30 and n equals 3. As we can see, both are similar. And in the second image, it represents the relative error for n equal 4 and n equal 12 till 35 for the left side and 12 till 37 for the right side. We note that the right curve is a straight line that deteriorates starting n equal 36. In fact, we can deduce from the right curve that for this example, the proposed method gives for n equal 4 acceptable results up to n equal 35 and beyond. From this value, the results begin to deteriorate. This phenomenon is related to the conditioning issue, which is well known for the Trapp's method. The slope of the line represented in the left side is equal to 2.69, which is numerically approximate the exact one equal to 2m out of 3, which is 2.66. Now we are going to consider a Laplace problem, which is the same as the previous problem, but with an additional term, delta p, where delta is strictly positive. In this part, I'm going to show you two ways to apply the Trapp's method. So the first way is by following the same steps as previously. So here it is the bilinear form ADG and the linear form L. We introduce then the variational formulation associated to the Laplace problem. So here, as we can see, we have this term in addition because of delta p. Then we apply the Trapp's method by considering first the space V of tau h, where the elements in this case are exponential modes, verifying the initial equation, and Vm of tau h is a finite dimensional space in V of tau h. And we define next the restriction AT on V of tau h. So here, the first two terms will be equal to 0, so AT will be equal to 3. To introduce next the variational formulation of the Trapp's discontinuous Galerkin problem. Then we define the following positive form, which is a norm on V of tau h. With this norm, we will follow the same guidelines of the previous problem to prove the coercivity and the existence and unicity of the solution. But in this case, we have an additional difficulty. It is in the a priori error estimate, because in this case, the shape functions are not polynomials, so we can't use the equality between the quadrature formula and the edge integral. But to treat this issue, some technical inequalities for exponential modes were introduced to obtain finally this a priori error estimate with the same upper bound of the error between the exact and numerical solution in norm DG as in the previous problem. This were also illustrated with numerical results by taking sinus x, the exponential square root of 2y as exact solution. Also, we can see that both images are similar. And here we represent the relative error for n equal 4 and n from 12 till 20 for the left side and 12 till 22 for the right one. And we have the same phenomenon in the right in the second figure as previously. We note also that the right curve is a straight line that deteriorates starting from n equals 21. And the proposed method gives for n equals 4 acceptable results for up to n equals 20, and beyond from this value, the results begin to deteriorate. So the slope of the line represented in the left part is equal to 2.70, which is numerically approach the exact slope, which is 2.66. And for the second way, I used the continuity relation using two parameters, C1 and C2. So after also integrating the initial equation by part and replacing pk and the normal derivative as shown in the previous slide, we obtained the following linear and linear form. To then introduce the variational formulation of the corresponding problem. Next, we apply the Treps method by considering the same space as previously. So here also, the shape functions are exponential modes to obtain the variational formulation of the TDG problem, where AT is the restriction of ADG in the space V of tau H. So here also, the first two terms will be equal to 0. Then we define the following positive forms, which are norms on V of tau H. Next, using the norms introduced in the previous slide, we prove the coercivity and the continuity of the Treps linear form AT on V of tau H to finally obtain the existence and unicity of the solution by proving its uniqueness and in finite dimensional space. And in addition, we have the following quasi-optimality formulation, and we finally established the a priori error estimate between the exact and numerical solution and norm DG, where the order in this case is m-3 out of 2, which is more effective. And in conclusion, so we applied the Treps method on elliptic problem. We saw that the Treps method is efficient because the number of basis functions is much less than the other methods. And the numerical results show the efficacy of this method. And as perspectives, what I'm actually working on is applying the Treps method on the same problem, but in the non-homogeneous case, minus delta p plus delta p equal f, carrying out the corresponding numerical study to then apply the Treps method on a Stokes problem. Here are some references. Thank you for your attention.
Thank you, Perla. Well, any questions from the audience? Okay, so please go ahead, Dr. Nassif.
Yes. Hi, Fatima.
Hi.
Thank you, Maha. Maria, I think.
Yes, Maria.
Yeah, okay, Maria, I want just to ask a question. What motivates the use of the exponential functions? What is the motivation for using, you replace the in the method, the polynomials by exponential functions, right?
No, the exponential functions are the basis functions because when the delta, wait.
But the basis functions now are non-polynomials, right?
Here, when delta is strictly positive, the basis functions here are not polynomials. They are exponential mode. That's why we have the difficulty because the quadrature we can't use the equality between the quadrature formula and the integral
But what is the motivation for choosing this form of the exponential? Any special?
This form comes from this
Are they
because
the condition?
They belong to the eigen functions or something, or
because they verify this condition.
I see. Okay, so they are like eigen functions or something. Okay, but now of course you say you reduce the number of degrees of freedom. You at the same time, if you replace polynomials by exponential, then the computation will take more.
Yeah.
Then I think, did you compare the time, the time of computations between the two?
The time, you mean the...
Does it increase the time? with respect to standard finite element polynomials, let's say.
You mean the time in the numerical result?
Yeah, time execution. Yeah.
Yes.
So did you do any comparison of the time that it takes to run the simulation with the other method versus the classical basis functions for finite elements?
Yes, it took more time, and yes, it took more than little bit more than.
This is the problem, that exponential are costly functions. So well, never, but anyway, it's very interesting. Thank you very much.
Thank you, Maria. Thank you for the question also. Let's move to our next speaker then. So we have Atiyah Eid. Please, can you try to share your screen?
Yes. I think I can't because Maria is sharing.
Maria, you have to stop sharing. Thank you. So, so Atiyah Eid from University of Rennes will be talking about explicit isogenies of large degree in small characteristic. So the floor is yours, Atiyah.
Okay, thank you for the introduction. I'm very glad to be here, and thanks for the organizer for putting together this event. So I'm finishing my PhD in mathematics in the Université de Rennes 1. And in this talk, I will present a brief introduction of the subject of my PhD thesis and some of our contribution. So I will begin with some definitions. So the first object that I want to talk about is elliptic curves. So first, we fix a perfect field K. So here we choose K to be perfect because the Galois theory over this kind of fields is simpler than over an arbitrary one. And we define an elliptic curve E to be a smooth projective curve given by a projective equation of this form. So here the coefficients of the curve are defined over the algebraic closure of K. And in order to write down the curve E as a set of affine points and points at infinity, we have to bring this equation to an affine one. So if we take an element in E and take Z equal to 0, then X should be also equal to 0. And therefore, the point that we obtain, the point 0, y 0, which is equal in the projective plane to the point 0, 1, 0. So E is a set of points in the affine plane, verifying this affine equation, plus the point 0, 1, 0, which we call the point at infinity of E. And note that when the characteristic of K is different from 2, then up to a change of variables, we can assume that A1 and A3 are equal to 0. And therefore, we obtain a simplified equation of our elliptic curves. So here are some examples of elliptic curves. So when K is the field of real numbers, one can draw an elliptic curve. We have two forms of an elliptic curve over R, up to a change of variables, depending on the number of roots of the cubic polynomial. So for example, here the polynomial has one root in R, and here the polynomial has 3 roots over R. So now for a finite field, an elliptic curve is represented by a point cloud. So for example, here every point has 2 coordinates in the field of integers modulo 1009. So why such curves are important in mathematics? So first, elliptic curves were introduced by Jacobi in the 18th century to compute elliptic integrals of this form. So here A and B are polynomials with coefficients in the field of real numbers, and A, B, and C are constants. A down-to-earth example is the sine function, and its inverse is the it is the arc sine function given by this integral. And an important application of elliptic curves in number theory was the proof of Fermat's theorem given by Wiles in 1996 that states that the equation xn plus yn equal to zn has no trivial integer solution when n is greater or equal than 3. And the last and important thing about elliptic curve is that their sets of points form an abelian group such that the point at infinity of the elliptic curve is the identity element. So this is how the group law in an elliptic curve is defined. So here, if we pick 2 points on the elliptic curve, P and Q, and we draw the line passing through these 2 points, and since the elliptic curve is a cubic curve, then this line intersects the curve at a new point, and the symmetric of this point that I denoted by R with respect to the x-axis will be by definition the sum of the 2 points P and Q. So the symmetric of R here with respect to the x-axis will be defined as its opposite for the group law. So with this construction, we obtain an abelian group. And when the field of definition of the curves is finite, we obtain a finite abelian group. Now we will see that the group structure of an elliptic curve allows us to do some cryptography. So cryptography is a method of protecting informations and communication through the use of codes. Here I will explain the Diffie-Hellman protocol. Alice and Bob would like to exchange top secret informations using a communication medium. As the nature of things are, Eve has a large interest in intercepting the communication that Alice and Bob send to each other. And so in order to secure their communication, they need to agree on a secret key. And to do that, Alice and Bob choose publicly a cyclic group G, for example, the group Z modulo PZ star. Then each of one choose an integer to be their secret key. So Alice choose A as her secret key, and Bob choose B as his secret key. Then Alice compute G to the power A and send it to Bob, and Bob computes G to the power B and send it to Alice. Then Alice uses the element sent by Bob and her secret key A to compute G to the power AB, and Bob does the same and computes also G to the power AB. So they obtain a common key, which is a G to the power AB, without each of them knowing the private key of the other. So this shared key will be used to cipher the informations, and the private keys A and B will be used to decipher. So here the elements that Eve can know are G to the power A, G to the power B, and G to the power A times B. So if Eve wants to know the private keys, she has to solve what we call the discrete logarithm problem. So formally, if we consider a cyclic multiplicative group G and an element H in G, so we call the discrete logarithm problem of H in base G to be the smallest positive integer n, such that H is equal to G to the power n. And the discrete logarithm problem is the problem of finding such an n. So a quick remark, so we show that an elliptic curve so it's over a finite field can be seen as a finite additive abelian group. So in the classical Diffie-Hellman protocol, Alice and Bob can choose the cyclic group to be a subgroup of the elliptic curve generated by a point P. And it is important to know that the DLP in an elliptic curve is much more difficult than the DLP in the multiplicative group Z modulo PZ star. So before I continue, I want to speak about a powerful tool that cryptographs are afraid of, the quantum computer. So as you know, the informations on the computer that we use right now, so the classical ones, are stored in bits. So they are represented either by 0 or by 1. But quantum computers can represent numerous computations of 1 and 0 at the same time. So here, for example, the sequence 0, 0 in a quantum computer can be represented in a classical one with the sequence 1, 0, 0, 0. So in general, a sequence of length n in a quantum computer is represented by a sequence of length 2 to the power n in a classical one. And this is why quantum computers are very powerful and more efficient than classical computers. And for example, the DLP, which is hard to solve in a classical computer, is easy to solve on a quantum computer. And for this reason, when quantum computers will appear, we cannot use the standard protocols like Diffie-Hellman, the classical Diffie-Hellman to cipher. So for this reason, another way to secure against a cryptanalytic attack by a quantum computer is to work with isogenies. So an isogeny between two elliptic curves is simply a morphism of curves and a group homomorphism. So when fixing a basis of coordinates, an isogeny takes the following form. So here F1, F2, G1, G2 are polynomials in the base field. And we define the degree of an isogeny as the maximum of the degrees of F1 and F2. And we say that I is separable if the order of the kernel of I is equal to its degree. So in order to compute the polynomials, F1, F2, G1, and G2, so in order to compute the isogeny I, it suffices to compute the four polynomials. And this is what we call a rational representation of an isogeny. So here, if we pick a field of characteristic different from 2, we can prove that an isogeny can be written of this form. So here H is a fraction of polynomials in one variable, and C is a constant. So if we fix two equations of E and E tilde, if we consider a generic point on E, for example, XY, the fact that its image by I is in E tilde gives the following differential equation. So if we know the constant C, which in some cases we can compute it, then we can reconstruct the rational fraction H by solving the differential equation. But there is a problem when we try to compute an isogeny, such that in particular when the characteristic of the field K is small compared to the degree of the isogeny. Because in this case, the differential equation that we want to solve has more than one solution. And this is due to the fact that the derivative of x to the power p is equal to 0 in characteristic p. So we lose some coefficients when trying to solve the differential equation. And in order to solve the problem, so what we do is we lift our differential equations to the field of p-adic numbers. So, so this is a definition of this field, and it is so this field is a characteristic zero field. So in it, p is different from 0, and also it is a local field in which we can define a norm and make it a Banach space. And in addition, as the field R, the field of p-adic numbers is an inexact field. So when doing computations in it, we can lose some precision. And what I can say here is that the loss of precision when computing the differential equations is already controlled when the field has odd characteristic. And in a paper that I wrote with my PhD advisors, we successfully treated the characteristic 2 case. So this is for elliptic curves. And now I'll explain briefly what we obtained for hyperelliptic curves. So first of all, a genus G hyperelliptic curve is a smooth curve given by an equation of this form. So here the characteristic of the base field is different from 2. But unfortunately, the set of points of an hyperelliptic curve does not form a group like in the elliptic curve case, but we can always associate with a hyperelliptic curve an abelian group called the Jacobian. So for example, in genus 2, the Jacobian contains a pair of points instead of 1 point. So if you want to define the group law on this Jacobian, we can construct it as we did in the elliptic case. But the difference, as I said, that an element in the Jacobian is represented by a pair of points on the curve. So therefore, we can also define an isogeny between Jacobians. And in order to compute it, we have to solve a system of differential equations of this form. And we have also the same problem when the characteristic of the base field is smaller than the degree. So I treated this case in 2 recent papers by also lifting the equation of the curve to the p-adics. And I will end the talk with 2 applications. So computing isogenies allowed us to compute efficiently irreducible polynomials of large degree over finite fields of small characteristic. And we obtained irreducible polynomials of degree up to 1 million in less than 1 minute. And also the computation, the computation of isogenies allowed us to compute contour division polynomials for hyperelliptic curves. So I think I'm done. Thank you.
Thank you, Ali. You just finished on time. So any questions from the audience? Please go ahead, Fida.
I'm not in the field, but I have a question for Eddie.
Yes.
When I guess we cannot always find the isogenies explicitly, right?
When the 2 curves are not isogenious, yes, we cannot find an isogeny, yes. So
is it enough to have some properties sometimes?
Okay, so in order to say that 2 elliptic curves are isogenious, so there exists an isogeny between the 2 elliptic curves, it suffices to, so we have proved that it suffices to show that they have the same number of points. So when they have the same number of points, in this case, we can say that the two elliptic curves are isogenious, and in this case, we can compute an isogeny.
Is this an obstruction?
No. It is it's a I think it's a theorem, and also just a little remark here. So when we want to compute the number of points on an elliptic curve, we have a powerful algorithm to do that. And so in a fraction of seconds, we can know if two elliptic curves are isogynous or not.
Okay, thank you.
Thank you, Ali. I guess we don't have any more questions from the audience. Thank you also for the elaboration that you just provided. I think it's time to leave for a lunch break, and then we join later. Thank you, everyone, for joining.
This session, just I would like to mention, directly after this session, you can select any can select any room, any breakout room, and join any room as you like. So now it's a pleasure to invite Professor Tony Sayah from the St. Joseph University, and he will talk about a posteriori error estimate and application of fluid mechanics. Professor Sayah, floor is yours.
Thank you, Tofi. I will try to share screen. Okay. It's okay. It's okay. You can see. Okay. Thank you, and thanks to all the organizers. Hello, everybody. In this presentation, I will talk about the posteriori error estimates and applications in fluid mechanics. The outline of the presentation is as following. I will begin with a definition of the posteriori estimates in general, and I will give some properties and a simple example, and I will show the adaptation strategy and different types of indicators. And next, I will give two applications in fluid mechanics. The first one is the Navier-Stokes system, and the second one, the coupling-Darcy concentration system. And I will end the presentation with the references, conclusion, and perspectives. Let us begin by introducing the a posteriori estimates. Let X a Banach space, be a continuous map on X, and F an element of F. We consider the following continuous problem. We have to find U in X such that A of U equal F. Here, F is a data, and U is the unknown. And usually we can imagine here a partial differential equation or a non-linear problem or any other problem. And as we cannot usually calculate the exact solution U, we have to approximate it by using some numerical methods. For example, the finite element method, the finite difference method, the finite volume method, or spectral method, or what any other or another method. We denote by H a real parameter, the parameter of approximation of the corresponding numerical method. And we introduce the following discrete problem. We have to find UH in XH, where XH is a finite dimensional space of X, such that AH of UH equal FH. Here, FH is an approximation of F, and AH is an approximation of A. And UH is the numerical solution, numerical corresponding solution. As we have an exact solution U and an approximate or numerical solution UH, we have to bound the error between these two quantities. Then we have in general two types of estimations, the a priori estimations and the posteriori estimates. The first one, the a priori estimations, in this case, we bound the error between the exact and numerical solutions with a quantity depending on the exact solution U of the parameter H and the data F. And here, as C1 depends on the exact solution U, it is not computable. And we cannot compute the right-hand side quantity. But here, if C1 and C2 are as H to the power of alpha, where alpha is a positive real, we talk about the convergence of the numerical method when H tends to 0, and alpha is the order of the convergence. The second, in the case of the a posteriori estimations, we bound the error between the exact and numerical solutions with some quantity, depending here on the parameter h, the numerical solution UH, and the data f. Here we can completely compute the second, the right-hand side, and this is the advantage of these estimations versus the a priori estimations. But it's not the only advantage. In fact, we have another one which will be exposed later. Let us now give some properties about the a posteriori estimates. If we use the finite element or the finite volume method, we can bound in general the error between the exact and numerical solutions with this quantity is a sum of eta k to the power of 2, where eta k is in general called indicators. In fact, this sum is a sum over all the elements of the mesh. For example, the triangles, and eta k is a quantity on each triangle k called error indicator, and it gives the error on this triangle. Now, if the constant A1 is completely computable, we talk about the guarantee of the upper bound. And furthermore, if we can bound each indicator locally around the triangle K with the error of the solution U minus UH, and also if we have that A1 and A2 are independent of H and U, we talk about the optimality of the a posteriori estimate. Now, furthermore, if A1 and A2 are independent of the data omega and F, we talk about the robustness of the estimates. Now, let us give a very simple example, the Poisson equation, to illustrate the a posteriori estimations. Here, we have minus delta U equal F, where F is the data, U is the unknown, and we have U equal 0 on the boundary of the domain omega. It's well known that this problem can be written in the weak formula, the following weak formulation. We have to find U in H1 0 of omega, such that integral of nabla U nabla V equals integral of FV for all V in H1 0. And to approximate the solution U, we use the finite element method, namely the PN Lagrange method. We have to find UH in H1 0H such that integral of nabla UH nabla VH equals integral of FVH for all VH in H1 0H of omega. Now, having the exact solution U, the numerical solution UH, we can easily show that the error between these two solutions can be bounded by this quantity, where eta k here is given by this formula. And here we have an error on the data F. Eta k, the first term of eta k is hk norm of fh plus delta UH. In fact, if we replace fh by f, UH by U, this term will vanish. Then eta k is really an indicator of error on the triangle K. We can apply the same remark. We have the same remark for the second term. Now, having all these indicators in all the mesh, in all the triangle of the domain, eta k is a good map of the error on all the domain. We compute. We can use this indicator in what we call the adaptation strategy. What is the adaptation strategy? It is an algorithm to adapt the mesh. In fact, we begin by calculating the mean value of all these indicators eta bar, and we apply the following algorithm. If eta k is greater than a constant Ca multiplied by eta bar, then eta k is big, and we have to refine the mesh around the element k. Ca usually equals to 1.2. Now, if eta k is smaller than a constant Cb multiplied by eta bar, Cb usually equals to 0.8, then eta k is small, and we have to coarsen the mesh around the element k. And for example, here we have a uniform mesh. After the adaptation strategy, we obtain the following mesh, where the mesh is concentrated in this region, where the solution is very important. The advantages of this strategy is that it allows us to get again in the memory size, and also in terms of the CPU time of computation, which is very important in industrial applications. Now, let us expose different types of the indicators. When we have a time-dependent problem, then the operator A is a time-dependent time and space operator. Then AH is a time and space approximation, and the indicator eta K will be divided in two parts. The first one, eta KH, which is the space indicator, and can be used to adapt the mesh as before. Eta K2 is the time indicator. We use this indicator to adapt the time step. Now, if we have a nonlinear problem, then the operator A is a nonlinear operator, AH is a linear approximation operator, and the indicator eta K can also be divided into two parts. The first one is like above. It's the indicator of discretization, and also can be used to adapt the mesh. The second one, eta Ki, is the indicator of linearization, and this indicator can be used to stop the iteration of the algorithm. Okay, now the first application is the Navier-Stokes equation. In fluid mechanics, we have omega is our domain in R2, and we consider the following system, where the first equation is the Navier-Stokes equation. The first term minus u delta u, when nu is the viscosity, is a given quantity of the fluid, u is the velocity of the fluid, it's an unknown. This term is the diffusion term. The second one is the convection term, u nabla u, and the third one, nabla p, where p is the pressure of the fluid, and also it's an unknown. F is an external force, which is a given function. And the second equation, dv equals 0, expresses the incompressibility of the fluid. The third one, u equals 0 on the boundary, is the boundary condition. And we have to solve or to compute the solution u and p. Now, this is a nonlinear problem because we have the term u nabla u. The corresponding weak formulation is the following. We have to find u in x, which is equal to h10 of omega to the power of 2, p in m equals to L20 of omega, and for all v in x and all q in m, nu nabla u nabla v plus u nabla u v minus div u v equal div vu, excuse me, here div v, not div u, div v p equals fv, and div u q equals 0. It's well known that this weak formulation admits at least one solution, and if under some assumption on the data f, this solution is unique. We have to calculate this solution u and p by using some numerical method. Here we will use the finite element method, and we have to approximate the velocity uh in the space xh, which is the space of the mini element, the space of functions vh, which is p1 polynomial of degree 1 plus bubble in each element, the pressure in the space mh, which is the space of the element qh, polynomial of degree 1 in h triangle, and the corresponding discrete problem is the following. We have to compute hph in xh multiplied by mh, such that for all vh in xh, qh in mh, we have the following system, which is analog to the continuous one by replacing u by uh and p by ph. In fact, this is a finite dimensional problem, but here this problem is still nonlinear because we have the term uh nabla uh, and we cannot compute. We have to linearize this term. To compute uh, we have to linearize this problem, and for that we introduce the discrete linearized problem. let UH0 a given initial guess, a given function, and at each iteration I, having UHI minus 1 from the previous step, we compute UHI PHI by solving this linear problem. In fact, this is a linear problem because the nonlinear problem here is replaced by this one, UHI minus 1, UHI, which is here a linear term because we know the quantity UHI minus 1. Now, having the iterative solution, we have to compute the indicators and calculate the upper bound. Now, for this problem, we have two families of indicators. Here, we have a nonlinear problem. Then we have the indicator can be divided in two parts. The first one, the linearization indicators, eta KIL, which is the difference between the velocity at the step I minus the velocity at the step I minus 1. The second part is the discretization indicators, eta KID, which has the following relation. Here, if we consider the first term, if we replace FH by F and UHI by U, PHI by P, this term also will vanish. Then this is an indicator of discretization, indicator of error indicator. Now, using these indicators, we can show the following upper bound. Upper bound, we can bound the error of the velocity and the pressure between the exact and the numerical solutions with this indicator up to an error on the data. And here we call this the upper bound, or simply the posteriori error estimates. Now, we need to show the optimality of this estimates. We can bound each indicator, the linearization indicator, locally at each triangle K with the error of the velocity on this triangle K. And also, the error indicator of discretization can be bounded locally at each triangle K by the error of the velocity and the pressure. Locally around the triangle K here, WK is all the elements around the triangle K. Now, bounding the indicator locally with the error allows us to show the optimality of the posteriori estimates. Okay, as we have an iterative problem, we have to stop the iteration at some level. Now, how we can stop the iteration? We have two kinds of stopping criteria. The first one, when the global error of indicator, which is the sum of all the error of linearization on all the triangles, when this quantity is smaller than some tolerance here, we take 10 to the power of minus 5. This is a classical stopping criterion. Now we have another kind, which is called new stopping criterion. We stop the iteration when the global indicator of linearization is smaller than a constant gamma multiplied by the global indicator of discretization, global indicator of discretization, which is a sum of all the indicators of discretization on all the triangles. When eta IL is smaller than gamma multiplied by eta ID, we stop the iteration, and gamma usually equals or smaller than 0.01. Let us show some numerical results corresponding to the Navier-Stokes problem. We consider an academic test case when we have here, and we perform numerical simulation by using the software FreeFM++. Omega is a square 0303, nu equals 1, UH0 equals 0, and we consider the following exact solution. U equal curl psi to have dv equals 0, where psi is a ball centered in the point 1, 1, and the pressure P is a cosine function. The exact velocity is like that, like this figure is a ball centered in the 0.11, and we begin we solve our problem by starting with this uniform mesh containing 800 triangles, and we apply the adaptive strategy from level to another. The first level of the adaptation strategy gives us the following: this mesh. We see here that the mesh is concentrated around the velocity, where the velocity is important. And from level to another, the second level, the third level, the fourth level, and from level to another, the mesh is more and more concentrated in the region where the velocity is very important. Now, to show the powerful of this method, we plot these two figures, these two curves in logarithmic scale. The error with respect to the global vertices number. The red one is the error by using the uniform mesh, only the uniform mesh. The green one is the curve of the errors by using the adaptive mesh strategy. And we see here that for a given number of vertices, the adaptive mesh, the adaptive error is very smaller than the uniform error. And this is we show here the advantage of the adaptive method versus the uniform method. Now, another application in fluid mechanics is the Darcy concentration coupling system. Here we have a time-dependent problem where the time is in the interval 0 big T. The first equation is the Darcy equation. Nu is the viscosity of the fluid, depending on the concentration C of the fluid. U is the velocity of the fluid. P is the pressure, and F is an external force, but here also depends on the concentration of the fluid. The second equation is expresses the incompressibility of the fluid, dV equals 0. The first two equations are the Darcy system, with which this system of equations in general is used to when we have a porous media. As the system is depends on the concentration, we have also the equation of the concentration C of the fluid. The first term is the time derivative. The second one is a diffusion term. The third one is a convection term, where the velocity U convect the concentration C. The fourth term is a reaction term, and G is a given function, external given function. The last three equations are the boundary condition on the velocity and the concentration, and the last one is the initial condition in the domain omega. Now we have to approximate this system. We use the finite element method, and the weak discrete scheme is the following. We discretize the velocity in the space of many elements, as in the case of Navier-Stokes problem. The pressure in the P1 finite element. The concentration is also in the P1 finite elements. And we use the following algorithm. Having the CH0, the initial value, and at each iteration n, having the CHN minus 1, we compute UHN, PHN by solving these two equations. And here we linearize the term by using CHN minus 1 to compute mu and f. Now, having UHN and PHN solution of this system, we put the velocity UHN in this equation to calculate or to compute the concentration. The time derivative is approximated by using the Euler method. Here we add this term, which is called the term of stabilization. At the continuous level, dV equals 0, but at the numerical level, dVHN is not equal 0. We add this term to have the stability of the equation. And here with a numerical test, we consider a numerical solution, which is a ball. The concentration is a ball walking across the diagonal of the square 0,303. And we see here that the mesh follow the concentration during the iteration, what we call the adaptation strategy. And we show here a comparison of the curves of the error curves in logarithmic scale between the uniform mesh and the adaptive strategy. And also here, the adaptive strategy gave an error very smaller than the uniform one. And also here, the adaptive mesh is more important than the uniform method. Okay, now we have a lot of works in progress in fluid mechanics. The coupling of time-dependent Navier-Stokes system with the concentration, the large eddy simulation for the Navier-Stokes system, the Darcy-Forchheimer system, the coupling Darcy-Forchheimer with the convection diffusion reaction problem, the Brickman-Darcy-Forchheimer problem, and other applications. But let us give some references in general. A lot of people worked in the posteriori estimations applied to the fluid mechanics, and namely Martin Voralik and co-authors, and also Gabriel Atiyah and co-authors, Vivek Giraud, and many other people. As conclusion, this technique, the adaptive strategy, is a powerful method, very important in the industrial application. It allows us to get a gain in the memory size and in the time of computation. And as perspectives, we can apply this method for other fluid mechanics, and why not for coupling problem of the fluid mechanics with the structure, with the wave problem, and other kind of problems. Thank you very much.
Thank you, Professor Sayah, for this nice lecture. Now we open the door for questions. So, any question? Yeah, Professor Nabil. Yes, Professor.
Hi, Tony.
Hey, hi, Nabil.
Yeah, it's just a question. When you use the last system with the concentration, do you have to introduce other indicators, or are they you don't have to?
Yes, here it's yes. Excuse me. Here I am very okay. We have two types of two kind of indicators. We have the time, the indicator of discretization, and indicator of iteration of iteration. I didn't put here the corresponding slide, but we have two types, okay? And as always, the discretization indicator is to adapt the mesh, is used to adapt the mesh, and the linearization, the indicator of linearization is to adapt the time step during the iteration, the time iteration.
Okay.
We adapt both the mesh and the time step.
Okay, thank you, Tony.
Okay, thank you, Nabil.
Any other question? So maybe I have one question. If we have different type of nonlinearity in one equation, do we have to introduce, for example, different indicator for each nonlinearity? For example, like u to the power p.
It's one indicator for all the linearity terms.
Even if we use the
if
different
if we have
two,
3 or 4 terms of nonlinear for nonlinear terms, that's the same. We have one linear indicator in each triangle and one linear indicator for of discretization in each triangle. Okay, we make all together. Okay.
Thank you.
Okay.
So we thank Professor Sayah for this nice presentation. Now we have to stop share now.
Yes, but stop share. Okay, thank you.
Now we pass to Michel Romanos from the University of Pulsars. Michel, it's your
Hi, can you hear me?
Yeah,
okay.
We hear you.
Okay, I'm going to try to share my screen. Can you see my screen?
Yeah, it's clear.
Okay. Okay, do this. Okay, so thank you everyone for being here and for inviting me to speak in this conference. So I'm Michelle Romanos, and I'm a PhD student in University of Pulsars in applied mathematics. So basically my work consists in developing mathematical macroscopic and microscopic models to understand how the embryo evolves during its development. And specifically, I will be interested in two tissues and how are they evolving in time and space. And throughout my PhD, I was also conducting my own biological experiments on the embryo to be able to better understand what my model does and how I can change parameters in my model and in my biological model also. So let's get into it. One of the striking events that interests us the most is the development of the embryo along its anterior-posterior axis. For example, you see here you have a human embryo approximately 2 weeks old that is a flat disc, and 2 weeks later it elongated, so it has a head and a tail. And this elongation is accompanied by the formation of two tissues that will be of interest to us, the paraxial mesoderm, which will be the future muscles and skeleton of the adult embryo, and also the neural tube, which will be the future nervous system of the embryo. So in order to study this elongation, we decided to take as a model the bird embryo. I don't know if you can see because there's a thing on top. Can you see everything?
Yeah, it's clear.
Okay. We use bird embryos because we cannot use human embryos to study this this elongation. So this is a movie I did in the lab where I harvested the quail embryo from the egg, and I put it on a gel and I film it overnight around 20 hours. And we see that we have a similarity with the human embryo. And we have the formation, so of the, I repeat, the tissues that are the neural tube, which is the central tissue, flanked with, on either side, on both sides, we have the PSM, the presomatic mesoderm, from on the right and on the left. And finally, one third tissue that will interest us also is what we call the neuromesodermal progenitor zone. It's a zone that contains undifferentiated cells that will give rise to cells to the neural tube and also to the PSM. So it will be giving cells to both tissues. So to be able to model this and mostly this posterior region that is elongating the most, if you see it in the movie, we decided to do like a mathematical cut on the most posterior part, just at the end of the neural tube, but right at the beginning of the progenitor zone, and also at the last somite, which is the equivalent of a vertebra, the last somite form, and we look at the evolution of those two tissues which are the neural tube and the PSM inside this posterior zone, and we will consider the progenitor zone as an incoming flux, so as a boundary condition basically, because its main role is to give rise to cells to both of these tissues. So the multi-tissue macroscopic model we developed is basically by considering two cell densities, N1 for the PSM and N2 for the neural tube, that are evolving in time and space. And both of these tissues are proliferating with different proliferation rates that have been documented. And we have them, this is actual biological data. And these proliferation rates are translated into the growth function G1 and G2, G1 for the PSM, G2 for the neural tube, that depend on the total pressures in each of the tissues, P1 and P2. And here there are many novelties in this model. For example, here the total pressure P1 is actually the sum of two pressures. The first one being the mechanical pressure, which is the pressure, which is the total pressure, a function of N1 plus N2. That is, so this is a novelty that because our mechanical pressure is actually singular at 1, so the total density cannot go above 1. And the second novelty is the repulsion term here denoted by N2QM and N1QM. So QM is the repulsion function that is function of the product N1 plus N2, N1 times N2. So here QM is here because this model actually promotes the segregation of these tissues. And the third novelty we've added to this model is that the velocities here follow the Brinkman law. And we use the Brinkman law for two reasons. The first one is because the neural tube is actually an epithelium. So the cells are quite, so it's very, very dense and the cells are really packed. So compared to the PSM, which is a mesenchyme where the cells are really spaced. So this creates a difference in the viscosities of both tissues. So this is why we use the Brinkman or Brinkman-Darcy law. And the second reason is that when we measured rotational movements, we saw that we had rotational movements in the embryo when we looked at cells, when we looked at the cells moving. So considering this velocity, this law for the velocity allows us to see rotational movements inside of the tissues. And the last novelty, well, it's not actually a novelty, it's a necessity, because when we add the segregation, we need to add also the fourth order term, which is the cohesion term, which is here to first penalize the high gradients of N1 and N2, because when we segregate, the gradients will increase. And also to create this cohesion, which means that the densities will prefer to segregate in packs and not in bubbles. And finally, as I said, we have some boundary conditions to complement this model, namely the boundary condition that is an inflow flux from the progenitor zone to both these tissues. So to locate our model in the state of the art in the literature. So the first models were, in the case of tumor growth, it was with Benoit Pertam et al. They developed a one species model that describes the growth of the tumor, and they used a power pressure law, so n to the power of gamma, not a singular law, which made them have an overlap of cells. So they allowed this, and also they used Darcy's law. Darcy's law being when you take beta equals to 0, so V is just proportional to the gradient of the pressure. Another model was developed by Nicolas Rochelet and Benoit Pertam, where they also described one species, the evolution of one species, but they used Brinkman's law. However, they made an important hypothesis, which is that the velocity is the gradient of a certain potential, and this makes the appearance of rotational movements impossible. So this is why we decided to keep the velocity as in this form. The third models from Brecht et al. And Carrillo, where they developed a two-species model, but the importance of these models is that they conserve something we call the segregation property, which is that when you start with two tissues initially segregated, they remain segregated for all positive times. The novelty of this model is that we can start with mixed tissue populations, population densities, and the model will segregate them. So this model is actually inspired by the thesis of Sophie Escht, and which she did with Pierre Dugon, and where they used this model, but without the Brinkman's law, they actually used Darcy's law. So to show you rapidly what this model does, namely the novelties of this model, so the Brinkman law and also the repulsion, I will go rapidly with one slide on the numerical method, because you see that this is a fourth order, those are the fourth order PDEs. And then I will show you some numerical simulations of what this model does. So I used a finite volume scheme that is flux preserving on a staggered grid for something that we call a relaxed model, inspired by a technique from Anina Shachtok that she did recently with Sophie Escht, which is basically we introduce two new auxiliary variables here denoted by C1 new and C2 new to relax the order of our model. So now you see that the two equations are of second order, and then we add, of course, two Poisson equations for C1 and C2 to be able to simulate this model. So let's look together at what repulsion does in this model. So here I prepared some simulations in 1D and simulations in 2D. So if we start with two densities here, the red one and the blue one, we see that if we the model will actually segregate them. So it's a very fast simulation. The model will actually segregate them, into packs. And then of course there's growth. So this is why you see that the densities are going. And if you look at it in 2D also, so we have the blue density and we have the yellow density that is denser. And we see that the model is very fast just segregates them and then it promotes growth. And finally, if you look at the difference between Brinkman's law and Darcy's law, so as I told you, when we consider the velocity as as proportional to the pressure, to the gradient of the pressure, we don't have any curl. So the rotational movements are null. Whereas when you consider the density as, when you consider the velocity as with Brinkman law, you have some, you have an increasing curl, of course, depending on the of course, if you choose some suitable boundary conditions. So basically, this is why we needed the Brinkman's law injected in our model, because we needed to take into account, so this is of course one species, but when you take into account two species with different velocity, with different viscosity parameters, you would see that you would need to take this into account in your model because it changes the dynamics. So what we did on this macroscopic model, first, as it's quite complicated, we reduced it to a one species model. We studied what we call the incompressible limit, which I will explain later. We study, so when we have an incompressible limit, we end up with a limit system. We study this limit system at equilibrium. We conclude another transmission problem from this limit system. And then I will go back to the two viscous, to the two species system I just presented, and then compute the incompressible limit on it. So what is the single species model? So basically it's like taking N1 equal to 0 in the previous model. So you don't need repulsion and you don't need the cohesion term. So you only need the evolution equation on N, and with the Brinkman law on V and the singular mechanical pressure. So this model, the system describes the evolution of the density. But what we want is, or actually another way to describe the evolution of this tissue is actually in a simpler way, which is basically by describing the geometric evolution, the evolution of its geometric boundary only, without really considering what's happening inside. So so this is a simpler way to describe the same tissue, and the link between these two descriptions is actually the incompressible limits. So it gives us, so we go from this model to something we call the free boundary model problem, which is when we can do this by taking epsilon going to 0. So when we take epsilon going to 0, you end up with another model at the limit, which we call the Healy-Shaw model. And you have an evolution equation on N, you have the Brinkman law on V. And if you see here on the left, if you multiply P by 1 minus N very formally, and you take epsilon going to 0, you would end up with this nice relation, P times 1 minus N equal to 0. And it is precisely this relation that will give you a free boundary problem, because you can define, for example, a domain where N is equal to 0, so P is strictly positive, and a domain where P is equal to 0. And so you would need to define inside of this moving domain omega of t, since P is strictly positive, you would need to define the dynamics of P, and through a computation, we can find what we call the complementary relation, which is divergence V equals G of P. And this will describe the dynamics of the pressure inside of omega of t. And one nice thing we can do, and this is of interest to us, is to determine the velocity of the boundary of omega of t to understand how it's moving, compressing, expanding, etc. So this is what we call the this is the incompressible limit we did. So we're ending up with a free boundary problem. And one thing we did is that we simplified it and we studied the limit, the same model, but at equilibrium. So dTn is equal to 0. You end up with a system on V and P here. And so now your domain is not moving, it's just omega. You can just define your system inside of a domain theta and R2. And in the case of a linear G of P, so if you take a really simple growth function and you inject and you play with your equations, you can end up with a system on V inside of theta. And as you see, the second order operator here has discontinuous coefficients, as you have the indicator of omega. So one of our main results was that in this case, where J is a linear function, we first showed the ellipticity of the second order operator here, which is minus beta Laplacian and minus 1 over J G gradient divergence. So the ellipticity of this operator depends actually on our parameters beta and J and G. And we also showed that the solution exists and is unique and is H1 inside of in theta. And the last thing is that we can show elliptic regularity, which means that we showed that V is actually smooth inside omega and outside of omega. It's smooth in every subdomain. And also it's continuous across the interface across the interface between omega and its exterior. So that's it for the system, for the velocity. Through a computation, we saw that we can actually get an equivalence of this problem to a transmission problem. So what is a transmission problem? It's exactly what you see in this figure. It's actually when you have two domains and your solution satisfies two different equations in the domain and in each of these domains. And there are you have some transmission conditions on the interface between these subdomains. And here, those systems are equivalent, and we see that our transmission conditions are, of course, the continuity of the velocity on the interface gamma that separates omega and its exterior, but also we have the pressure, the jump of the gradient of the velocity that depends also on the pressure jump here. So this is P, but you can see because this is G of P, this is P based on the expression of G of P we gave, the linear one. So what is interesting is that in this case, the pressure is discontinuous, and we saw it when we had the transmission problem. And this is very distinct from Brinkman's law, because in Darcy's law, the pressure is actually continuous. So as I told you, we have a domain where P is strictly positive inside and P is 0 outside. Well, actually in Darcy's law, it's P is 0 on the interface, but here it's not. So we have a discontinuous pressure. So this is one of the interesting dynamics we get when we look at this transmission problem. And finally, if we go back to the two species viscous model, what we want is also to be able to describe the dynamics of these two tissues in a simpler way, so only by geometric evolution of the tissues, of the boundaries of the tissues. So in the same way, we not only take epsilon going to 0, but we also take m, the repulsion parameter, to infinity, and alpha, the cohesion parameter, to 0. And the same way we obtain, so I don't have much time to describe this, but the same way we obtain an incompressible, a Healy-Shaw system with the same relation here that allows us to define not only, to define a moving domain, but also we obtain a really nice property, which is the full segregation of these two tissues when m is equal to, when m goes to infinity. And we can also compute the velocities of the exterior boundaries and also of the interface in any of these two cases, if one is inside the other or if they share an interface. And we are now doing some simulations on FreeFEM to better see these dynamics. And to conclude with the numerical simulations on the embryo, one nice thing we can do is to simulate in the same way a neural tube in the middle with a PSM on the left and on the right. And here we have so this is the density plot. So we have a high density here next to the vertebra, and you have a lower density in the posterior. And we can look at the density plots, and also we can look at the fluxes. So we can really look at many different quantities from this macroscopic model. So this is before the limit, of course. And one hypothesis that we see that we can, one preliminary hypothesis is that we have the differential proliferation we put, so because we put different proliferation rates for each of the tissues. And the injection from the progenitor zone play an important role in those tissue dynamics. And to conclude, one thing I want to do this year is that I want to test this hypothesis, and I can do that by actually injecting, so it's electroporation technique. So we inject the DNA with a protein called P27, which will be a cell cycle inhibitor. So it will inhibit the proliferation in either or in both tissues. And finally, I would like also to investigate the injection of the progenitor zone inside the tissues by also electroporating proteins that actually inhibits cells inside the neural tube and inside the PSM. Thank you for listening.
Thank you, Michelle, for your presentation. Any question? Any question?
Yes.
Yes, Professor Sayah.
Michelle, hi.
Hi.
Yeah.
Michelle,
yes. Can you put please a slide when you replace the Darcy equation by the Brickman equation? At the beginning, I think.
This one?
Yes. Okay, here we can see that the second equation, the right one, is the Navier-Stokes equation. Without Navier-Stokes equation, no? No, yes, we have plus V. Plus V yes. Instead of UV and nabla V. Okay. Yes. Have you seen what happened if you put if you insert the Brickman Darcy for Shamer's equation?
I haven't looked at that. It's one of our.
It's important because when we have a porous media,
yes,
and the velocity is important, it's useful to put the Forshamer term, and it's important, but because it will let you see the rotational terms, if you have another term, another phenomena in the fluid.
Yes. Okay. Other than.
But it's a non-linear term. It will complicate the equation. Sure.
Yes. Yes. It's already complicated. So.
Have you at what level you have the theoretical results?
What do you mean?
In your work here, it's only numerical work?
No. This is just numerical. This is the theoretical part where we study.
Okay. Can I have another question to Faye or what?
Yeah.
Okay. The epsilon, when you tend epsilon to 0, what is the physical phenomena here? What we have exactly here as okay?
It's basically when you I mean how we can understand is basically when you take the density to its maximal packing density. Here it's 1. So here it's basically when you take epsilon to 0, we see that the density will reach its maximum packing. Here we put it as 1, so the density will only take either 1 or something else outside.
And,
so basically
and
like
p epsilon, which is equals to epsilon eta over 1 minus eta.
Yes.
N over 1. When epsilon tends to 0, p epsilon tends to what?
P epsilon is this is exactly the this relationship we have here. It's very interesting
because very difficult here to see what happened if epsilon tends to 0.
Yes. Okay. So let me just explain fast. Here actually the P you see is correlated. It's very correlated to N, the density. But when you tend epsilon to 0, you lose this correlation. P is actually decorrelated, so you need another equation. So actually P, something very interesting happens that P is decorrelated, so you need either P is 0 or you need another equation.
Okay, so for that you put P empty multiplied by 1 minus equals 0.
Exactly.
Exactly. Okay.
Exactly.
Okay. Thank you.
You're welcome.
Okay, thank you, Michelle, for your presentation.
Thank you.
Now we pass to Bishara Saadi from Insaran.
Hello.
Hello. You can share your screen, please.
Yes. Fine. You see the screen?
Okay.
Oh, okay. Hello, everyone. I'm Shara Saad, a PhD student in applied mathematics and mechanics at INSA Duran and St. Joseph University of Beirut. The topic of my talks today is on energetic approach for formulation of metallic materials constitutive models. The presentation is divided into 4 main sections. I will start first with to present the main goals of this work. Then I will introduce some work using energetic approach, and after I will apply the energetic approach to the classical plastic law, and finally I will present the developed energetic kinetics differential equations. Let me start with the objective of this presentation. Why we use law in mechanics? We use law in mechanics to describe the mechanical behavior of materials. So we can also predict the behavior of the materials in a forming process with varying conditions. We can express sigma in terms of strain epsilon to describe the forming process of metallic materials, for example, in 3 phases: elasticity without form changing, plasticity when the volume of metallic materials change, and saturation is the final shape of the material. In this work, the main idea is energy. We use the definition of energy that gives a relation between W, sigma, stress, and plastic deformation, and it's represented by the hatched area in the figure. So we can express now sigma function of W, energy. Why you want to express sigma function of W? Because this expression, sigma function of W, give all the physical mechanism govern to change the microstructure of materials. In other words, if there is the reason of deformation in materials, not only the result of deformation like the classical one, sigma function of epsilon. Let me now introduce some work using energetic approach. One of the widely used law for elasticity is Hooke, given as follow. Give a sigma function of epsilon. It's based on energy. Using the potential energy psi, expressed as follow, and by differentiating psi with respect to epsilon, we can retrieve the well-known elastic Hooke law. The same thing in hyperelastic law. The hyperelastic law define first energy, the strain energy, and the general form of this law is given by this formula. By differentiating energy W with respect to deformation tensor C, they can we get the hyperelastic law. Now, I will return to this work. I apply energetic approach to the classical plastic laws. Before I present the work, I will give an equivalence between plastic law, energetic plastic law, and the classic plastic law. The classical formulation of plastic laws expressed as sigma function of plastic strain epsilon, reversing this equation and differentiating with respect to sigma, and after considering this function and recalling the definition of energy W, yields to the energetic law sigma function of energy W. The inverse of this approach is shown by Shirakashi et al. Giving sigma function of W, we can, by reversing, differentiating, and separating terms and integrating using the definition, we can retrieve the classical law sigma function of plastic strain. Well, now I will apply this approach to the widely used classical plastic laws, Holomon, Krupkowski, Ludwig, and classical voice law. Starting with Holomon law is given by the following expression, reversing this equation and differentiating with respect to sigma, integrating and using the definition of W, energy, we can get the relation between sigma and energy W. So the equivalent stress sigma is in terms of the dissipated plastic energy W, N prime and K prime are the constant parameters of the materials. Likewise for Krupkowski law, expressed as follow, expressing plastic strain and differentiating with respect to sigma, and after integrating using the definition of energy, we can get the relation between sigma and energy, and thus we can obtain the energetic law as follows. The same thing applies also to Ludwig law, given by this expression. It's equivalent to this equation also, differentiating with respect to sigma, and by integrating, we can obtain the energetic law sigma function of energy. For the classical voice law, expressed as follow, we express the plastic strain from the above expression, and now by differentiating and integrating, we obtain this equation. By using variable change, it can be easily shown that the integration gives this equation. And by assuming that U is from this form, we can obtain this relation. Now, to obtain the solution U, I used to define a function, number function. The number function gives the inverse of U times exponential U, and it's defined on -1/e to plus infinity. This function cannot be expressed in terms of elementary function. It's only represented by numerical points value and can be done by a graph. This graph, the red part of this graph is for negative values, and the blue part of this graph is for positive value. That's all I want to say about number function. Now return to our expression. To solve this expression, the analytical solution is given by this system, U, and we can find now the energetic voice law expression, sigma function of W. Now let's get to energetic kinetics differential equations for the same laws. Holomon law, we express Holomon as follow, differentiating with respect to W energy and differentiating phi with respect to W. And by adding initial conditions, we can retrieve or we can obtain this system. And the solution of this system is exactly the same energetic law given before. Now for Krapkowski law, we express Krapkowski law as follow. First, we differentiate W to sigma with respect to W, and we differentiate also phi with respect to W. By adding initial conditions, we establish the energetic equations. And the solution also of this system gives exactly also the same energetic law given before. For Ludwig law, expressed as follow, by differentiating sigma with respect to W, differentiating phi with respect to W also, adding initial conditions, the solution of this system give exactly the same one, the same energetic law given before. For the classical voice law, we construct a system differentiating sigma with respect to W, differentiating phi with respect to W, and by adding initial conditions, the solution of the system gives the energetic law also. Conclusion. The main point of this presentation first is present all the work based on energy approach, and second, apply this energy approach to the classical mechanical behavior laws, and third, we develop constitutive energetic models for hardening law. Thank you for your listening. I'm ready if you have any questions.
Thank you, Shara, for your presentation. Now I'll pass the question. Anyone has question? Yeah, Professor Sayyah.
Yeah. Hi, Bshara.
Hi, hello, Tony.
Bshara, I see here a lot of models. Okay.
Yes.
What is the difference in the physical term between a model and another? Because we have a lot of equations, okay, but physically, what is the difference between these models? Okay.
Okay. We have difference in mathematical form, yes, only, yes. By adding exponent or exponential or plus constant or like this to predict or to describe the mechanical behavior of materials. By using energy, we generalize all the law.
Okay.
This is why we use energy to not use a lot of law for the same materials, the same metallic materials, for example.
To describe better the model, the system, or
better.
We have other phenomena, other things inside. What? That's
yes. For the classical one, they add parameters for every phenomena. Mm. By using energy, we use the reason for this phenomena. This is why we don't have to add parameter n, for example, a constant from here, exponent
because excuse me, Bshara, the study, this energy study is a global study. That's not local study. We study the energy of all the systems.
Yes, but the energy,
but it's not macroscopic. It's, I think, I'm not okay in this field, but I think it's a global study. No, not microscopic study.
It's generalized. Yes, it's not. It's microscopic also, microstructure.
It's microscopic also?
Yes. Why? Because energy is divided by plastic energy, for example, also thermic energy.
Okay.
No, this one.
Thank you.
In this presentation, we use also only the plastic energy.
Okay. Thank you.
Other question?
Probably I have one comment. I think the constitutive laws that you discussed, Bshara, usually are derived from the microscopic properties of the material by some kind of asymptotic analysis. So you start from a micro scale and you get these constitutive laws that you mentioned after asymptotic analysis, no? And these are macro scale models, no?
I use the equivalence between classical one and energetic one.
Mm-hmm.
Classical one, a part of classical ones are based in are physically based, and the other parts are only mathematics expression.
Okay, thank you.
To modelize the curve in the first.
The active, the stress-strain relation, you mean?
Yes, this figure. Sorry. The first one.
Okay, other questions? So I have a one question. So
yes.
You treat the elasticity and plasticity and saturation as I see in this figure.
Yes.
So what about viscoelasticity? Can we predict the viscoelasticity by using the energy?
Yes, I see
can
it
model
in
the viscoelasticity from several mathematical models.
Yes, we can define the energy by adding terms of viscoplasticity. By adding a term in energy, we can get the law, the behavior law of materials with viscoplasticity.
Okay.
It's clear for you. It's clear for you.
Now, Dr. Joanna.
Yes, hello. I just wanted to say something about the microscopic and macroscopic behavior. Actually, these laws, as someone said, are derived from the microscopic behavior, but they describe the macroscopic behavior once we obtain them. So what we have here is the macro, not the microscopic. Just to be clear for that.
Okay, thank you, Bshara.
Thank you.
Now we pass to George Saman.
Hello everyone.
George Saman is a PhD student from the St. Joseph University.
Yes, hello. I'm George Saman, PhD student at St. Joseph University under the direction of Professor Tony Sayah from St. Joseph University and Professor Fawzi Triki from University of Grenoble. The title of my presentation is Finite Element Methods for the Darcy-Forchheimer problem coupled with a convection diffusion reaction problem. I have it. Just one second, please. So first, I will introduce, in section 1, I will introduce the problem. And in section 2, I will present the results concerning the existence of solutions. And we proved the regularity and uniqueness of the solution under some additional assumptions on the data. In section 3, concerns the discretization of the problem using a finite element method. The finite element method is a general numerical method for solving PDEs in 2 or 3 space variables dimensions. So to solve a problem, the method subdivides a large system into smaller, simpler parts that are called finite elements. This is achieved by a particular space discretization. So the method approximates the unknown functions over the domain. So we consider the Darcy-Forchheimer problem coupled with the convection diffusion reaction problem. The system P is the system of equations. The first 2 equations in system P represents the Darcy-Forchheimer problem with the boundary condition on U, while the third equation is the convection diffusion reaction. We suppose that omega is a simply connected open domain in R2 or R3, and we suppose that omega is bounded, having a Lipschitz continuous boundary gamma with a unit outer normal n. The unknowns here are the velocity u of the fluid, its the pressure P, and its concentration C. The parameters rho, mu, and beta are positive constants, and they represent respectively the density of the fluid, its viscosity, and its dynamic viscosity. Beta is also called the Forchheimer coefficient. Since when beta is equal to 0, the first equation becomes the classical Darcy's one. But Forchheimer showed that when the velocity of the fluid is higher and the porosity is non-uniform, Darcy-Forchheimer's equation is more adequate than Darcy's one to describe the creeping flow of fluids in porous medium. The diffusion coefficient alpha and R0 are supposed positive constants. The function f, depending on the concentration, represents an external force acting on the fluid, and the function g represents the external source. The K inverse is the permeability tensor assumed to be bounded and definitely positive. Assumption on the data. We suppose that the function f, we have that f depends on the concentration, can be written as follows. F of xc is the f0 of x plus f1 of c, where f0 is a given function in L3 over 2 of omega, and f1 is a Lipschitz function from R into Rd, satisfying the following inequality. We suppose also that the concentration source G is in L2 of omega, and that K, the permeability tensor, satisfies the following bound, where Km and K big M are 2 strictly positive constants. The weak formulation associated to problem P is find the velocity in L3, the pressure in the Sobolev space W1 3 over 2, which is the space of functions in L3 over 2 of omega, and their first derivatives in the weak sense also in L3 over 2. The concentration in the Sobolev space H10, which is W120, such that we have the following 3 equalities. We note here that concerning the pressure, if P is a solution to the problem P, then P plus any constant is also a solution, since here there is a gradient of P. So to guarantee uniqueness of the pressure, we must add an additional condition on the pressure. So we suppose that the pressure must belongs also to the space of zero mean value. And we note here finally that problem VA is equivalent to problem P. Each solution to problem VA is a solution to problem P using Green's formula. Now, in order to prove the existence of solution, we have to simplify problem P to obtain a simplified problem or a reduced problem. So first, we studied Darcy-Forchheimer problem, and we have the following theorem. For a given function f in L3 over 2, the Darcy-Forchheimer problem has a unique solution UP in these spaces. Proof, first we have the following if-soup condition, which can be easily obtained by remarking that the space L3 over 2 is the dual space of L3. So using Rie's representation, we can easily obtain this condition. Now, using the if-soup condition and Babusca-Bressis theory implies that the Darcy-Forchheimer problem is equivalent to the following. Find a solution U in the space V, which is the space of vectors in L3 with the divergence free, such that for all V in V, we have the following equation, where the operator A is a map from L3 into its dual space, defined as for each V, we have A of V equal mu over rho, K inverse V plus beta over rho norm of V times V. We have the following properties for the operator A. A, as I mentioned before, A maps L3 into its dual space and is stable. The operator A is monotone from L3 into L3 over 2 and satisfying the following inequality, where C1 is a strictly positive constant. A also is coercive in L3 and is semi-continuous. So now, using these four properties of the operator A, the Minty-Broders theorem implies that the operator A from V into V star, its dual, it's surjective. And as the function f is given in L3 over 2, which is contained in V star, so there exists U in V such that the Darcy-Forchheimer problem has a solution. Finally, the uniqueness of the solution is obtained from the monotonicity of the operator A. Now, using the last theorem, we can split the problem P into the following. Find a concentration on the Sobolev space H10 of omega such that we have the following equation, where U of C is the unique velocity solution to the Darcy-Forchheimer problem with a fixed C. And now I will present the first main result. Theorem 3, problem P admits a solution UPC in these spaces and satisfying the following bounds. For the proof here, we worked on the reduced problem and we used a Galerkin method with a fixed point theorem. The three bounds here are easy to check. Regularity and the uniqueness of the solution. If we suppose that now that that omega is regular and that the concentration source is bounded over omega, then we prove that the concentration solution is also bounded over omega and satisfies the following bound, is uniformly bound. And we have theorem 5. In addition, if we suppose that the function g satisfies the following bound called the smallness condition, then the solution of problem P is unique. Discretization of problem P. We assume now that omega is a polygon in 2 dimensions and polyhedron when d equals 3. And we consider a regular family of triangulations th of omega satisfying the following 2 points. The closure of omega is the union of the triangles, and the intersection of 2 triangles is either empty, a common vertex, or an entire common edge. I also introduce the finite dimensional discrete spaces, XH, MH, and YH. The discrete spaces, the velocity is discretized in the discrete space XH, which is the space of functions continuous on the closure of omega, and the restriction on each triangle are polynomial of degree 1, plus the basic bubble function, which is the product of barycentric coordinates. For the pressure and the concentration, they were discretized in the space of functions continuous on closure of omega, and the restriction are polynomial of degree 1. We have also the discrete variational formulation. The weak formulation can be discretized as following. Find a discrete solution UH, PH, CH in the discrete spaces such that we have the following three equations. Here we introduced this term to stabilize the equation. Existence of a discrete solution. The discrete problem has at least one solution satisfying bounds similar to 2. Moreover, if the discrete problem has a solution such that the discrete concentration satisfies the following bound, then we prove that the discrete solution is unique. For the proof here, we used an easy finite dimensional theorem of theorem 3. Then after this, we showed that the discrete solution of problem VAH converges when H goes to 0 to the exact solution of problem P. And now concerning the priori error estimates, under assumption 1, if we suppose that the solution of the exact problem satisfies the following regularity. If C is in the Sobolev space H2, P also, and the velocity in the Sobolev space W13, and if the concentration satisfies the following condition, then we have the following a priori error estimates. We remark here that the rate of convergence for the concentration in H1, the velocity in L2, and for the pressure in L3 and W1 3/2 is equal to 1, while the rate of the convergence for the velocity in L3 is equal to 2/3. Finally, numerical investigation were performed to confirm the theoretical accuracy of the discretization. First, we linearized the problem P, since the problem P is not linear, and we showed the existence of linear solution. Then we showed that the linear solution of the linear problem converged to the exact solution of problem P. And the numerical rates of convergence for the concentration, for the pressure, and the concentration were approximately the same as the theoretical ones. We used free fm plus. And as a conclusion and the future work, so in this work, we considered the convection diffusion reaction problem coupled with the Darcy-Forchheimer problem by an external force who depends on the concentration. We established the existence of solutions using a Galerkin method, and we proved uniqueness. And we proposed and analyzed a numerical scheme, and we derived an optimal a priori error estimates. In my future work, I will work on the bifurcation of solutions. I will suppose that the function G, the source G, doesn't satisfy the smallness condition. So we don't have necessarily the uniqueness of the solution. So I will study how we can compute many solutions and if we have uniqueness on any subdomain. And finally, I will start the posteriori analysis associated to problem P. Thank you for listening, and I'm ready for questions.
Thank you, George, for your presentation. Now we pass to question. So any question or comments? Yes, Dr. Fatima?
Thank you for the presentation. I just have one question. Probably this is common also to Professor Sayah. You're always using a bubble function in your finite element, in the finite element space that you are using. Why is this the case? So we have this basic bubble function. Wouldn't the P1 be enough?
No, P1 couldn't be enough since we must add some conditions to guarantee that divergence will be equal to 0.
Mm-hmm.
We must add some equations. The bubble function is the product of barycentric coordinates.
Okay. Thank you.
Thank you.
So I have a question. So why you select the space L3? Why you didn't use, for example, L2?
L3. Okay.
So I noticed that
Okay.
all your work was based on L3.
Why not? Yes. Why not L2? Regarding here the first equation, the Darcy-Forchheimer equation. So the nonlinear term, we have norm of u times u. If we multiply by a function v, then the integral is not defined if u is in L2. So if u is in L2, so norm of u times u will be in is not in L2. Yani. Here is if u is in L3 and norm of u is also in L3. So norm of u times u will be in L3 over 2. So if we multiply now by a test function also in L3, the integral will be defined since we have duality between L3 over 2 and L3.
I see, yeah. So due to nonlinearity in this case.
Yes. If we had the Darcy-Forchheimer...
but you can attack your problem in another point of view. For example, you can linearize your problem and return to the nonlinear problem. In this case, you can omit the condition L3.
Yes, we linearize the problem in the numerical...
I am talking theoretically, and you can, instead of theoretical of a nonlinear problem, take a linearized problem, then return by some limit to the nonlinear problem. So I don't know if this strategy works or no, but this will help you to eliminate the problem of L3 spaces.
Okay.
Another question also, I noted that here you take the temperature constant, I think.
Can you repeat, please?
So you didn't take into consideration the temperature. Why?
No, here the problem doesn't depend on...
yeah, and you say that the temperature is constant.
No, here we can, the same problem, the same equation here can be coupled for the Darcy-Forchheimer with the temperature. It's sufficient, it's sufficient to set R0 equals 0 and replace C by T.
Okay, I see.
Okay, and we got the heat equation.
Also, the coefficient alpha is constant in your case?
Yes, yes, alpha is the diffusion coefficient.
Because in general, the diffusion coefficient maybe depend on the velocity itself or the pressure. Okay, thank you. Any other question or comments? So at the end, I would like to thank you, George, for your presentation.
Then Nadine Dirani, then Samara Shamoun, and then Samer Dweck. So the order of the speakers will be slightly modified, and also Nadine was supposed to speak earlier in session 2, but it was necessary to switch, and so I will in any case announce again as soon as we have any readjustment of the lineup for this afternoon session, just last minute change in the order of the lineup of the speakers. So actually, let me remind again, after your talk, Then there will be the talk of Nadine Dirani with a new order of Samara Shamoun, and then Samer Gweik will speak third. Okay, so this is the only updates that I needed to. So I think that we should actually start. The right time is approaching. So it is really with great pleasure that I announce the talk of Filippo Sant'Ambrogio from University of Lyon, and he's going to talk about Sobolev spaces and Wasserstein distances.
Okay, so thanks a lot, Beppe. Thanks for introducing me. Thanks to all the organizers of this meeting for inviting me. It's really an honor and a pleasure to be here in this meeting of the Lebanese community, and I mean, I'm happy that you invited me to be part of it. So I will present. So it will be a short talk on some topics which are related to my main area of research, which is optimal transport. And in particular, we present some answer to some questions. Some are more recent, some are older, related to the connection between optimal transport distances and other form of distances, in particular related to Sobolev spaces. So I will start. I'm not able to change the page. Why? Ah, yes. You don't see the picture. Sorry. I think I just come back to the previous file where you should probably be better able to see the picture, even if the, yes. Okay. So I'm sorry. Anyway, it seems it's quite fine. Anyway, so. I start from a very short introduction to what is optimal transport. It's a problem which dates back to the 18th century when Gaspard Monge, a French mathematician interested at the time in military applications, he asked a very simple question. Suppose that you have a certain distribution of mass that in modern mathematical language you can say that is mu on a certain space X, that you have to move and you have to obtain a prescribed distribution of mass somewhere else, Y. Then in our case, we will be more interested in the case where X and Y are the same space. So I call it omega, and you can think of a domain in a Euclidean space. And you have to move to choose where to bring each particle in such a way that you minimize the total cost. So you have a cost C of xy is the cost per unit mass to move something from X to Y. The typical case, the case that Monge had in mind, was the distance between X and Y. We will also be interested in cases where you take the power of a distance, but keep in mind that it's something related to the distance. And in modern mathematical language, you are given two measures. You look at all the maps which send omega into omega, which transform the first measure into the second one in terms of the image measure, and you minimize this cost. Now, for this problem, there is a long history because, by the way, it is not obvious at all that there exists an optimal T. Anyway, many progresses have been done when Kantorovich, a Russian mathematician, more interested in application of mathematics to optimal use of resources, of logistics, he also got the Nobel Prize in economics, proposed a different formulation, essentially of the same problem, just you change the language. Instead of describing the movement by saying for every X, what is your destination T of X, you consider all the pairs X and Y, and you describe your movement by saying for every pair X and Y, how much mass goes from X to Y. And of course, you accept the answer 0 if no mass goes from X to Y. In the previous configuration, for every X, you only send mass to T of X. But here you're a little bit more free. You can send also masses to different locations, and then you take the average cost. You integrate the cost C according to a probability measure on the pairs, with some constraints. The fact that the image measure according to the first and the second marginal, the first and second variable, should correspond to the constraints mu and u that you have. Now, the advantage of this problem, which is in some sense an extension of the previous one, is that you can easily prove existence by means of weak compactness of spaces of measures. It is a linear programming problem because the constraints and the function are linear in some infinite dimensional setting, but you can also imagine the case where mu and nu are discrete, and this really becomes a linear programming problem in finite dimension. And in some cases, but I will not insist on this, in some cases, you can prove that the optimal gamma here is actually concentrated on pairs xy, where y is a function of x. So you can come back to a solution of the Monge problem. In some cases, I'm not so much interested because I'm much more interested here in this talk in the value of this optimal cost and not in what is the optimal solution. So one of the properties of the fact that this is a convex optimization problem is that there exists convex duality, which allows to write the minimal value as the value of another optimization problem, which is a maximization problem with a dual structure. Here I minimize over measures. Measures are the dual of continuous functions. And so the dual problem will become a maximization among pairs of functions, phi and psi, with a constraint, phi plus psi is smaller than c, and you maximize the average value of phi and psi. So you try to have phi and psi as large as possible, but you cannot too much because of this constraint. Now, and this is really something which is quite standard in convex duality and in particular linear programming. This is also another linear programming problem. The unknowns are phi and psi with linear constraints. And you can see that this cost C, here it was in the functional to be minimized. Here is in the constraint. Mu and nu were in the constraints. Now they are in the function that you try to minimize. Now, with this optimization problem in mind, you can construct a distance on the space of probability measures. Now you can, in the sense that you choose as a cost the power of the distance. You take the minimal value and then you take power 1 over p, exactly as we do for LP distances. But there is a strong difference compared to what we do with distances in LP. Imagine that you which is really a difference of flavor. Imagine that you consider two different densities, the blue and the red one. An LP distance is in some sense vertical. For each x, you look at how much vertically the two graphs differ, and then you take an average of this value. So you consider what's the vertical distance between the two graphs, and then you take the average value. Here in the Vasten distance, which is the name that it is given to these distances, you try to have an idea of horizontally how much you should move the first graph to obtain the second. Of course, in this precise example that I made, a translation is enough. If the two graphs are not one the translation of the other, this map will not be, the distance between x and t of x will not be constant, and you will have to take an average. And you can prove on a compact space that this defines a distance, and the converging according to this distance is the same as converging in the weak sense of probability measures. Now, there is another interesting property, either in the definition, in the value of the distance, but also in the properties of this metric space, which is a dynamical interpretation. Actually, you can prove that the Vasten distance, now WP to the P means take the optimal value they defined before. Don't take the power 1 over P because you raise again to power P, is also equal to a minimum of another optimization problem where now you integrate in time and space and you look at all possible interpolations which go from the original measure mu to your final measure nu with a family of curves rho t, and sorry, a family of measures which will be a curve of measures rho t. This curve of measure will be forced to satisfy a PD, which is called the continuity equation, which is very classical in mathematical physics. It just describes the fact that V is a velocity field which moves the mass of rho. And this is the PD which comes from conservation of mass. And among all the pairs, rho and V, which satisfy this PD, which means that they are a feasible movement in the physical space, and which have initial and final configuration which are prescribed, you minimize a sort of kinetic energy. If you take P equals 2, this is really the kinetic energy, mass times velocity square. And you can prove that this value is the same as the previous one, which in some sense here I'm integrating in time an infinitesimal version of the previous one, since I'm taking an LP norm of the velocity instead of an LP norm of the displacement. And here, this formulation is also very useful for doing numerics. And here I show one of the first numerical simulations which are obtained by Benamou and Brenier, where you see the initial measure here is the let's say, sort of Gaussian centered in some point of a torus. And what you see here, there are 4 parts of the same Gaussian. So essentially, it's again the same Gaussian, but it is centered instead of in the center of the torus in the corners. And you see what happens in the movement. You see this measure rho t, which evolves from one configuration to the other. Now, the measure rho t, which solves this, is actually geodesic, a constant speed geodesic in this Vasten space connecting mu to nu. And you can also find it explicitly if you know the optimal map T in the optimal transport formulation. Now, a natural question when you have this kind of distances on the set of measures is to compare them to distances, to other new distances. But I insisted that they have a very different nature than LP distances. And by the way, they metrize weak convergence and not strong. So in general, it's they will be probably much smaller than some LP distance between the density of mu and the density of nu. So the good way is to compare it rather than to LP distances to negative norms like W minus 1p norms which are in the dual of some functional spaces. So you can start from the simple case where you take the cost to be the distance. So essentially you take the exponent p equals 1. You look at the dual problem, and a computation which you can do very easily is, suppose that you give phi, what is the best possible psi? You look at the best possible psi is the largest one which satisfies this constraint. And so you can see that you have an expression that is psi should be the infimum of c of xy minus phi of x, but c is the distance. So you can see automatically that this should be an infimum of one Lipschitz function. So you can see that there is no reason to choose phi and psi which are not one Lipschitz. If you choose an arbitrary phi, you replace psi with a one Lipschitz function, then you fix psi, you choose the best phi, you get both of them which are one Lipschitz. And you can see that once one of the two is one Lipschitz, if you do again the formula inf c of xy minus psi, you get the opposite. So inf of distance between x and y minus a one Lipschitz function is exactly equal to minus the one Lipschitz function. So this means that you can restrict the previous maximization problem to the case where one function is one Lipschitz and the other is the opposite. So essentially you have the W1 from mu to nu is the sup of the integral of phi integrated according to the difference among all one Lipschitz functions. So it means that this means that the dual norm, actually this is inequality, actually the dual norm in the space, the norm in the space of dual to Lipschitz function is exactly equal to W1. So when you integrate an arbitrary function phi according to mu minus nu, this result will be smaller than the Lipschitz constant. So let's say, okay, you have to be in a convex domain, let's say the L infinity norm of the gradient times W1. Now, here you have a 1, here you have an infinity, and 1 and infinity are dual to each other. So a very natural question is, can we generalize this kind of inequality to other inequalities involving other LP norms on grad phi and other vast distances here? So maybe LP here and LQ here if the Q is the dual to P. Now, this cannot work in general. This cannot work in general because if you take functions which are in W1Q in a Sobolev space, so with a certain integrability on the gradient, but not enough, smaller than the dimension, then these functions are not continuous. In general, there are functions which are not continuous, so you cannot integrate according to arbitrary measures mu and nu, while even if my pictures showed densities, you can also imagine that you have a Dirac mass and so on. If mu is a Dirac mass and phi is not a function which is well defined in every point, this inequality has no hope to be true, has no hope to have a meaning. But maybe we can have some inequalities like this if we add some assumptions on mu or nu or both. So now, let's come back a little for a while to the geodesic that we obtained from Benamou and Brenier, because so far I didn't use this dynamical interpretation. And there is a fact that I should have put a citation also to this effect proven by McCann, a fact which is the following. If you take the LR norm, so let's say the integral of a density to power r, so what I mean is take a measure rho, suppose it is absolutely continuous, and integrate its density to power r. If it is not absolutely continuous, take plus infinity. Now, this is a functional defined on the space of probability measures, and we look at its properties along geodesic. So I take a rho t, which is one of these special geodesic found by this dynamical interpretation of optimal transport. And what happens is that this norm is always convex along this geodesic. It means that if you take the, so this is not the LR norm, it's the LR norm to power R. So anyway, you can see that the LR norm of a rho t will be smaller than the maximum between the initial and the final norm. So you can also send R to infinity and get that the L infinity norm is smaller than the maximum between the two intermediate infinity norm. Now this is useful because you can now take a test function phi, you integrate according to nu minus mu. You see it as the integral in time of the derivative of integrating according to rho t, because this is the final value, phi d nu, minus the initial value, phi d mu. Now you use the equation on the time derivative of rho t, which is dt rho was the opposite of a divergence. You replace it with the opposite of the divergence, you integrate by part, the divergence becomes a gradient, and so you get grad phi dot the velocity field d rho. Now, you do a Hölder inequality in this space integral, taking a grad phi to the power p prime and a v to the power p but the LP norm v to the power p d rho is exactly equal to the Western distance. And since it does not depend on time, you can also take it out of the integral. So in the end, you have this difference of integrals is more than the Western distance of order p times the integral of the gradient of to the power p prime d rho. Now, if you didn't have this d rho, you would have a Sobolev norm of phi. Now, since you know that rho is bounded in L infinity, if you suppose that both are bounded in L infinity, you know that also the intermediate measures are bounded in L infinity by the same constant, and you say you can bring it out of the integral, and you get a nice inequality, which is that this difference of integral is bounded by a constant depending on the infinity norm times Western distance time the Sobolev norm of phi, exactly with the exponents in duality. But you have to pay this price, the assumption that you are in L infinity. You can generalize if you insert an extra exponent. I don't do the computations, but if you suppose that they are not in L infinity, but they are in some certain LR space, then you don't exactly arrive at WP and W1Q. You have a P, a Q, which have to have a certain relation with R, and you can see that if you put R equals infinity, you get the usual relation between P and Q. Now, this kind of computations with P equals 2 and applied to some PDEs where the density was supposed to be and was naturally bounded were developed for the first person who developed it was Grégoire Lepère in a paper about Vlasov-Poisson, so a paper about PDEs where he needed to have a bound on a kind of integral like this. Essentially, this is an H minus 1 bound in terms of a Western distance. The generalization, you can, for instance, find this generalization as an exercise in my book on optimal transport. Once, of course, the easy case with L infinity has been developed in the main part. Okay, so this means that if both mu and nu are nice, then you can get an improvement of your, so a generalization of your W1 L infinity estimate. Can we do something with a one-sided estimate, in the sense that I suppose that just one of the two is nice and the other is not? And the case that I have in mind, that actually it's not my idea, it's a case which was discussed by this colleague, Stefan Steinenberger, who is a colleague, let's say, from harmonic analysis. He had in mind the fact that very often we want to discretize integrals, which are, let's say, integrals according to the Lebesgue measure, with finite sums. So the typical case is that mu is a uniform measure on a domain and nu is an atomic measure. And typically this atomic measure is on a grid, for instance. Now, if you suppose that you have points on a uniform grid, so if you put n points, the step between the distance between one point and the closest one is of the order of n to the power minus 1 over d. And if you compute the Western distance to the uniform measure, you get n to the minus 1 over d, whatever the p is, in the sense that if the points are so much uniformly distributed, whatever the LP norm that you compute, you get more or less the same result, because it's like computing LP norms of a function which is almost constant, so it doesn't change so much. So because of this, he says, let's suppose that we are in a configuration where it is not the P of the Wasserstein, which is a problem. So let's take the best possible Western distance, the largest one, the W infinity, which I didn't define, but you can define W infinity instead of being the minimum of an LP norm of the displacement, it will be the L infinity norm of the displacement. So a possible definition is that you take the L infinity norm of transport minus identity, or L infinity norm of X minus Y, L infinity according to the measure gamma on the product, or you can also prove a dynamical formulation, the L infinity norm of V under the constraint of the continuity equation, which is what is the minimal maximal value of V, such that you can connect mu to nu with a curve rho t with velocity field V. Now, you can do the same argument where phi d mu minus nu, you differentiate here, you get this result, but now the first thing that you do is that you bring the L infinity norm of V out, and so you get L infinity norm of V times the integral in time, integral in space of modulus of grad phi d rho t. Now, then you integrate in time, essentially you change the order of the integration, you define a measure M, which is just the average of the rho t. And so if you know something about the integrability of M, then you get, then you just put the LP norm of M and the LQ norm of phi with the corresponding P and phi, and you get a result as you want. Now, what can you say about the integrability of M? A first reasonable fact is that suppose the the easiest but worst case. Suppose that, because we saw that if both measures are nice, then rho t stays nice. So the worst case is imagine that the target measure nu is 1 Dirac, which is the most concentrated one. So it means that rho t will concentrate around one point. And so essentially it is an homotopy from the original mu to the Dirac. So you can just see by some scaling arguments that rho t will be concentrated on a scaling of the support of mu, and the density will increase, and you can compute exactly at which rate, and it will be a negative power of 1 minus t. When t tends to 1, this will be 0 to a negative power, so you will have infinite densities. Now, you can compute exactly what is the power. It depends on the dimension and the dual of R. And so you can see that this quantity is integrable in time if this exponent is less than 1. So if R prime is, so d over R prime should be small, so R prime should be large, so R should be small. Exactly, R should not increase the dual of the dimension, d over d minus 1. So a first result that you can get is this one. This difference will be smaller than W infinity times an LP norm, and then you take the dual norm. But what you need is that this P prime is smaller than R prime, so that P is larger than the dimension. So you can get an inequality like this with a constant which degenerates where P tends to the dimension. This is true. Now, this colleague was quite annoyed by the fact that this inequality was not one inequality, but a family of inequalities depending on P. You cannot find a precise space where to put, and there is a constant which explodes with P. And you also had an intuition. The intuition is that look at your measure M, which is a density, if you suppose that mu is the uniform measure. You can compute it by integrating these homotopes, and you compute that it explodes at 0 exactly as the power 1 minus d. Now, this is exactly the limit exponent not to belong to this LD prime, because if you take this to power d prime, which is d over d minus 1, you exactly get the minus d, which is exactly the non-integrability exponent dimension d. But it belongs to a space, what is called the Lorentz space. The space is LPQ, are defined as the space where the measure of the level sets have a certain to power 1 over P has a certain integrability. And this here, what you're saying is that the measure of the level sets are bounded by a constant over a certain power of the threshold that you take. So you can define, this is infinity and this should be 1, sorry. You can define actually the LP infinity norm as the sup of a certain comparison between the measure of the level set and the power of the set that you take, and the LP1 should be a certain integral, and there are all the LPQ in between. And actually what happens is that these spaces LPQ are in duality with LP prime Q prime. So if this one belongs to LP infinity, so to LD prime infinity, you can expect here to put LD1, the dual. So LD1 is a norm which is slightly larger than LD, and LD P prime infinity is slightly smaller than LD prime. So the conjecture is, can we put a constant W infinity, and here we put LD1 without putting coefficients which explode. Now, this can be done, and it can be done in this way. You can see that actually it's even more general. You can see that if mu is a constant, then you have this rho t, which are just an homotopy, and you can explicitly compute, at least in the easiest case, or otherwise you can generalize, compute what happens to this density, and prove that it belongs to LD prime infinity. You can do it in the case of one point. You can do it in the case of a finite number of atoms, if nu is a finite number of atoms, and then you do it by approximation. Now, here there is a small loss in the sense that, remember what I said here is, if mu is in a layer, then M is in the same layer if R is smaller than D prime. If you take R equals D prime, you lose something. You have to suppose that you are in a layer 1 in order to obtain that you are in a layer infinity. This is the loss. This loss is essentially sharp, because if you take mu to be exactly the density of this form, x to 1 minus d, and you compute the corresponding m, which is the integral of all the homotopes, there is a log which appears. So it has a slightly higher explosion in 0, so you cannot hope to have something which would be bounded in L infinity in the same way. Now, This sentence is essentially for Samer, and actually in the previous slide there is also an advertisement for Samer, even if it is not related to the talk that he will give today, that Samer worked exactly on, which are the LPQ summability results for what is called the transport density, which was something that I treated here, which is really based on integrating this rho t. And in some sense, this result means that I can also obtain a critical result, which is not included in Samer's paper, because in order to only have assumption of mu, not on mu, you really need P to be smaller than D prime for the most of the classical assumption. This is a very slight improvement, but I must say for the transport density, I don't know if this is sharp. Anyway, what I get is exactly this, that if you start from a measure mu, which is in LD prime 1. So what does it mean? It means that it has a certain integrability of the measure of the level set. For instance, a uniform measure, but this is much better because uniform measure means an infinity, but essentially it is applied to the case of uniform measures. And if I have a measure nu which is arbitrary, for instance, an atomic measure, and atomic measure is the typical case to which we apply it, then we can bound this difference of the integrals with the LD1 norm of the gradient, the vast and infinity distance, and of course a constant which depends on dimension and on the initial norm. So this proves the conjecture. Of course, what I presented here in order to do a recent result, so this is not even written, I should find the time to write and to detail exactly this proof, which actually requires to improve a little bit the technique, in the sense that instead of doing a time derivative, I will do differences between a finite, between a countable sequence of times, because otherwise I have some technical difficulties. So you have to improve a little bit the technique. I want to present an overview of which kind of questions you can ask in comparing vast and distances to dual of Sobolev distances, dual of Sobolev norms, and of course, these could have applications in different settings. For instance, the first application by Grégoire Lepere was an application in PDEs, because once you have this kind of estimates, then you can use them, for instance, in improving uniqueness result when you try to do a Lagrange lemma, typical technique to prove uniqueness for equations which have a form of this form, a continuity equation with a V which depends on rho, is that you differentiate in time the vast distance, and then you need some inequalities. And in order to get that finally something is smaller than the vast distance itself, it's nice to have inequalities of this form. The application here was more an application for having precise bounds on the error that you have in integral discretization in sampling. So I think I stop here, and I thank you for your attention. And I'm of course available if you want to know more or if you have questions.
Thank you so much. Thank you so much, Filippo. Then we have a few minutes for any questions. The floor is open for that. If anybody would like to ask some question, you can raise your hand on Zoom. Okay, I see there is one from Samer to begin with. Can you unmute yourself? Okay.
Yes. Okay. Hi, Filippo.
Hi, Samer.
Thank you for this very nice talk. So just I have a question about this sharp result in the critical case, I mean, when P is the dual of the dimension. So if we improve the regularity of the target measure nu, so can we prove in this case some better estimates on the measure M or the transport density?
So you mean if you suppose that nu is better than just arbitrary?
Yes, but always
but nu is only D prime.
Yes, exactly.
I don't know, because I remember that in the so in my paper here there was an intermediate result when if you suppose different integrability exponents for mu and nu, you can get something which is in between. And you're right, I didn't try. I'm okay. I'm not so sure that with these techniques this could work, but I don't know. I don't know actually. Yes.
Okay. Thank you.
All right, is there some other question now? Let's see, I'm not sure that I'm seeing some other raise hand. Also, I am trying to keep the schedule here, which means I believe that already at 5:45 we are starting a new talk. So I think this is really the time. Thank you so much. And okay, so I will then leave the floor to Nadine Dirani from University Côte d'Azur, Nice in France, who's going to talk about contact between the formal solid and a rigid fixed wall.
Yes, thank you for the presentation. Hello, everyone. First, I would like to thank you for the invitation. And today I would like to present my work on the contact between a deformable solid and a rigid fixed wall. So first, I will start by I don't know if you see my screen, it's moving.
It's moving now? Yes.
So I will start by a motivation. The effect of explosion on structure is a major point of interest in risk and safety analysis. The impact of explosion has twofold. The first hazard originates from overpressure effects, and while the ballistic projection, as we see here in this figure, of solid parts can be equally dramatic. So for the contact problem, I will start by introduce the elastodynamic equation in strong form, which consists in finding the displacement U such that we have rho U second minus divergence of sigma equal to F, where rho is the density, U second is the velocity, sigma is the stress tensor, and F the external force. I would like also to define the strain tensor epsilon U with the following expression. And we have the Hooke law, which connects the stress tensor sigma with the strain tensor epsilon by the following expression. So we have sigma, it's equal to lambda trace of epsilon identity plus 2 mu epsilon, where lambda and mu are the Lemmy coefficients. And finally, we have the stress tensor sigma u can be written as C epsilon u, where C is the fourth order elasticity tensor. So now we're adopting the following notation for the normal displacement and the normal stress by taking the tangential complement is equal to 0 for the sake of simplicity. So as we see in this figure here, this figure formalizes our problem. So we have an obstacle, the obstacle in gray at x equal to 0, and we have a solid with domain omega comes into contact from the positive side, and the domain of omega is decomposed in 3 parts. So we have the Newman condition, the Newman boundary, the Dirichlet boundary, and the contact boundary, which is in red. So for the contact, we use the Signorini condition, or what we can also call unilateral contact condition. So the first condition is the non-penetration condition. Here we have the normal displacement is greater than 0. The second condition says that we have compression of normal stress. And the last one, the complementarity condition, says either we don't have contact, and in this case, we have the normal stress is equal to 0, or we have contact, and in this case, we have compression of normal stress, so we have sigma n is greater than 0. So this graph here shows the strong nonlinearity of the contact law, which we hard to be taken into account. We also define the bilinear form A and the linear form B, L as follows. So now let us define the unilateral contact problem. So the unilateral contact problem consists in finding the displacement U such that we have divergence of sigma U plus F equal to 0. We have sigma U, it's equal to C epsilon U, and we have the displacement, it's equal to 0 on the Dirichlet boundary condition, and we take on the Newman boundary condition, the normal stress is equal to 0. So let us talk now about the space discretization. So first, the solid is discretized by a finite number of rigid particles, and we use the discrete element method, which is adapted for problems presenting singularities as contact problems. So here we have two types of degrees of freedom. We have the sense degrees of freedom, which are the red points, and those are the displacement field placed at the pericenter of each cell. And we have the green points, which are the boundary faces degrees of freedom placed at the boundary of the solid. So what we want here is to reconstruct a displacement on the interior face. So we want the blue points. To reconstruct those displacements, what we do is we take a triangle which contains the center of the interior face. So the edges or the vertices of the triangle are the cell's degrees of freedom. And now we can compute the reconstructed displacement or the interior degrees of freedom by barycentric interpolation. So once now we compute the reconstructed gradient, the reconstructed displacement, we can construct a discrete gradient on each cell. So the discrete gradient is the sum over the faces setting on the boundary of the cell of the reconstructed displacement tensorial, the external normal of the face, weighted to the area of the face over the volume of the cell. So using now the reconstructed gradient here, we can obtain the discrete strain tensor. For the bilinear form, it's classic. So to obtain the expression of the discrete bilinear form, we just replace the continuous strain tensor in the bilinear form by the discrete strain tensor, which is obtained from the reconstructed gradient. In this type of problem, we have jumps on cell faces. That's why we have a scheme which is not stable. So to obtain a stable scheme, what we do is we add a term of penalization for the discrete bilinear form to penalize the jumps on cell faces. So for the moment, we talk just about what we do when we don't have contact. So when we have contact, we have a dichotomy between Newman boundary condition or Dirichlet boundary condition. So between no contact and contact. So if we have Dirichlet boundary condition, in this case, we impose the displacement on the boundary faces degrees of freedom. While when we have Newman boundary condition, in this case, we should solve a local problem on the boundary faces degrees of freedom to check condition on normal stress. That means to check if we have compression of normal stress. Here, the advantage of our method is that our boundary faces degrees of freedom have no mass. And so there is no dynamic on the boundary faces degrees of freedom. For the time discretization, we use the MEM scheme. The MEM scheme is an explicit pseudo-energy conserving second-order time integration scheme for Hamiltonian dynamics. So the scheme works for any Hamiltonian dynamics in slipped form. What we mean by slipped form is that the Hamiltonian is decomposed in two parts. The first part is the kinetic energy, and the second part is the potential energy. Here we have Q is the position, and P is the momentum, with P equal to mv, where m is the matrix of mass and v the velocity. Now for the dynamic equation, we have Q point, the inverse of the matrix of mass multiplied by P, and P point is minus the gradient of the potential energy, which is equal to the force applied to the position. Now for the MEM scheme works classically. So it's like a leapfrog or a Verlet scheme. So first, we update the position. So we have Qn plus 1, it's equal to Qn plus delta T m minus 1, Pn plus 1.5. And the second step, we do a different thing. So here we do a two-step scheme. That's why we have here n plus 3.5 and n minus 1.5. So we have the integral from 0 to delta T to the force applied to the position, which is linearly interpolated in time between Qn and Qn plus 1. So that's what we wrote here exactly. So we start by Qn when tau is equal to 0, and when tau is equal to delta T, in this case, we obtain Qn plus 1. So now we can obtain, we have the integral of the force, and if the integral of the force is exact, in this case, we obtain a pseudo energy conservation with the following expression. So for example, if we have a force which is linear and continuous, in this case, for example, we can do a midpoint quadrature and we can integrate it exactly. While in contact case, we have discontinuities in the force. And so the previous strategy doesn't work. That's why what we do is we propose a modification of the MEM scheme. This modification consists first in identifying the discontinuities, then in detecting the contact time. So once we have the contact time, we can make a quadrature before and after contact, and then we can integrate the force. Regarding the numerical results, the first results about the Hertz contact. So we take a disk of Hertz with radius 20 centimeter, and we take a vertical force on it. And we have the lower boundary of the disk. We take the lower boundary of the disk as the contact boundary, and we take a Newman boundary condition on it. So when the disk is moving and comes into contact with the obstacle in x equal to 0, we have a concentration of normal stress in the area near to 0, and this concentration decreases when we are far from 0. We have a deformation of the shape of the solid, and the solid stays at x equal to 0 because we impose the non-penetration of the solid in the obstacle. And this result is compared to a reference solution with color plot of von Mises stresses given by Franz Schully in 2019. Now we take a bounding ball. So we take a ball with initial velocity, and we have an obstacle at x equal to 0. And so when the ball is moving, it stays in contact a few seconds. We have a concentration of normal stress. We have a wave which propagates into the wall, and we have a deformation of the shape of the ball. In another case, test case, we take a beam, and this beam will bounce on the obstacle. Here, the obstacle is taken, it can be taken either in x equal to 0 or in other position. So when the beam comes into contact, so we have here in blue and red, we are showing the velocity. And so we have a wave which propagates in the beam. And here we have a dispersion phenomena due to the space and time discretization. And here finally, we have done the contact with the two deformable solid. So it was a little bit harder than the obstacle because we have to take into account the position of the two solids and the contact between those two. So when we have contact, here we have deformation of the shape of the solids, concentration of the normal stress. And as we see, we have this shape of the two empty balls is like that because we impose the non-penetration of the two solids. So as a result, for all the previous test cases, here we obtain an exact conservation of energy when we have contact. And that's because we suppose or we propose a modification for the MEM scheme. If we don't identify the contact time, in this case, we obtain a bad convergence even if we increase an order. So finally, to end with the perspective, we can do this thing for several deformable solids, and we can improve the order for large deformations. In the previous work, I just worked for small deformations and small displacement. And my actual work is about adding a fluid between those two solids and trying, when having contact, to evacuate the fluid out of the zone of contact. Thank you for your attention.
Thank you very much. Thank you for the nice talk. Once again, the floor is open for questions. So if you want to ask any question, you can raise your hand through Zoom. Of course, if you wish, you can also independently write in chat if you have some doubt, some question afterwards.
Sorry, Giuseppe.
Yes, okay.
Ahmad.
Yes, I didn't see the hand. Okay.
Hi, thank you for your talk. Just a question about the point of contact. Is it always like always smooth, or can be concentrated at different point on the solid?
No, it can be on different point on the solid. For example, here, the zone of contact is all of this zone here, for example.
Which is kind of continuous, yes? I mean, but...
Yes, it's continuous.
Okay, so it's always like this, yes?
Yes.
In your example concept. Okay, thank you.
You're welcome.
All right. So is there any other question? I hope, by the way, you cannot hear too much noise on my side, hopefully, because I realized that now the commencement exercises have started just outside of my office. So I will try not to create too much noise. All right, if there is no further question, then I would already thank you so much once again for the presentation. I would then leave the floor to Samara, just to see, first of all, if the share screen sharing is working correctly.
Hi, yes, can you see my
Hello?
screen?
I think we can see too much.
Okay, what about now?
Okay, this seems to be correct now.
Yes.
Let's wait just one additional minute though, just to be in line with the schedule. I never know if someone is maybe joining slightly, maybe exactly at the moment where the talk is starting. So let's. But it seems everything is working very, very nice also with the connection today. So that's well, something to be pleased about, I would say. It's not always completely a given. Okay, maybe you heard that the music stopped, and I think this was actually connected with the with a short power cut that we are having now. Okay, I believe, however, that we can actually start. So once again, I'm happy to introduce Samara Shamoun from Michigan State University, and she's going to talk about a new phi convexity result of the bilateral minimal time function for nonlinear control system. So please, thank you.
Thank you. Thank you so much. Hi, everyone. My name is Samara Shamoun. I'm a second-year PhD student in the Department of Mathematics at Michigan State University. I work in control theory. First, let me start by saying that I'm very happy to be here today. It was really nice to hear all the amazing work and research done by fellow mathematicians. It was also really nice to see some familiar faces. Today, I'm going to present a work done by Shadi Noor and me about a new phi convexity result of the bilateral minimum time function for a non-linear control system. So the outline of the presentation is going to be the following. First, I'm going to start by some general definitions. I want to focus in particular on semi-convexity and phi-zero convexity. I'm going to introduce next the problem, the differential inclusions, define the bilateral minimum time function, and then state some of the regularity results that were actually in the literature for the bilateral minimum time function. At the end, we're going to state the main result and maybe have a quick slide about the sketch of the proof. Okay, so let's start. First, dsx denotes the Euclidean distance. This is the projection of a point into a set, and this is the notation for the proximal normal cone to a set at a point. It's always easier to see things geometrically. So let's see, if we have a set S, how can we find a proximal normal vector? So how can we find a vector that belongs to the proximal normal cone to a set at a point? So this is the question, how can we find this geometrically? The idea is very simple. All we need to do is actually find a ball whose center is this point S plus R psi over norm of psi being the vector, and the radius is R, so we are looking for this R. And the idea, we want to find such a ball whose intersection with the set S is equal to empty. So if this is possible, the vector psi is called, it's realized by an R sphere, and it belongs to the proximal normal cone to the set S at S. Okay, if this is not possible, like this case, let's look at this point here. We see that no matter how small the ball we take, it's always going to touch S from one of the sides. So the proximal normal cone to the set S at this point is actually going to be 0, because we can never find a vector that is actually realized by an R sphere, no matter how much we take R to be small. So let's keep in mind this ball characterization of the proximal normal cone to a set. Now, two very important definitions are semi-convexity of a function and phi-zero convexity of a set. First, let's start by semi-convexity of a function. So we say that a function f is semi-convex if for every x0 in x, we can find two constants, delta and c, such that the following inequality holds true for all the points x and y in the neighborhood of x0. And here, let's pay attention and notice that this constant c is actually uniform. So it's the same constant for all the points in the neighborhood of x0. Actually, semi-convex functions are quadratic perturbation of convex function. So if I have a semi-convex function, let's say f is a semi-convex function, this would tell me that f plus c over 2 norm of x squared is convex. So as we can see, since semi-convex are just some quadratic perturbation of convex, they inherit a lot of regularity property from convex functions, such as local Lipschitz continuity or almost everywhere twice differentiability. And the second definition is the phi-zero convexity of a set. So we say that a set S is phi-zero convex if we can find a constant such that the following inequality holds true. Again, whenever we are dealing with a set, it's always easier to see things geometrically. So it's the same thing here. So let's see, how can I, using some figures, how can I know if a set S is phi-zero convex or not? So this is what I should do. I should take all the points x in the boundary of S. I should take all the proximal normal vectors to these points, and I should see if all these proximal normal vectors are realized by spheres of the same radius, then the set S is phi-zero convex. If it's not possible to do that, then the set S is not phi zero convex. For example, let's look at the first one. As we can see here, as long as we're moving to this point here, we have to reduce the size of the ball. So we can never find a radius r such that all the psi are realized by this r sphere. Hence, the set S is not phi zero convex. Let's look at the second example. Actually, S is convex. S convex means S is actually zero convex. So this phi zero here is actually zero. What does this tell me? This actually tells me that you can take the size of the ball to be as big as you want, and it's still going to work. So the normal vectors is realized by an R sphere for every R positive. It's still going to be done. So let's keep in mind this idea of semi-convex functions and phi zero convex sets. A very important remark. So like I said before, F semi-convex means F implies F is locally Lipschitz. Something else, what is the relationship between semi-convex and phi zero convexity? The idea is if we have a convex, semi-convex function, the epigraph of this function is going to be locally phi zero convex. So this is the relationship between these two definitions. And one can ask, what about the converse? And actually, the converse holds true. If I have a function whose epigraph is phi zero convex, if I add the assumption that F is Lipschitz, then this would give me that actually my function is going to be semi-convex. This remark is very important. We're going to use it later in the talk. Okay, so let's start with our problem. As we know, optimal control problem can be given by differential equations or by differential inclusions. When we talk about optimal control problems given by differential inclusions, it means instead of having an equation here, or instead of having a function, we have a multifunction. So multifunction, it maps points to subsets instead of mapping points to points. So we're going to work with differential inclusions. This is our problem. And let's define the upper Hamiltonian to be this. Through all the presentation, we're going to assume that our multifunction F satisfies the following. We call them standing hypotheses, denoted F. So I want for every x, f of x to be non-empty, compact, convex. F is locally Lipschitz, and I want the multifunction F also to satisfy the linear growth condition. Now that I defined the problem, let's talk a little bit about what is the bilateral minimal time function. To be very concise, if I have 2 points, and if I want to find the bilateral minimal time function between these 2 points, this is what I should do. Let's find all the times that starts with 0. So we're going to start with, at the time 0, we're going to start with alpha. And at the time t, I want to reach beta. As long as the trajectory from alpha to beta, I want it to satisfy the differential inclusion. So let me take all these times t, and let me take the infimum of these times. This is what I'm going to call the bilateral minimal time function between 2 points. Now, one can ask the question, what if we don't have a trajectory that satisfies the differential inclusion? In this case, by convention, we take t alpha beta to be plus infinity. Something else we should pay attention to is the effective domain and the sub-level set of a bilateral minimum time function. So those are given simply by these 3 definitions. Okay, we define something called small time locally controllable at beta. We say that a multifunction f is small beta STIC, or small time locally controllable at beta. This is if and only if t dot beta is actually continuous at beta. So we're going also to use this definition a lot. Now we're ready to talk a little bit about some of the regularity results that were actually in the literature before this work. So let's talk about the continuity of t dot dot. T dot dot is continuous in the domain if and only if it's continuous at every point of the diagonal. And this is also true if and only if f and minus f are both STLC at beta for every beta. For the pointwise continuity at alpha beta, I just need the STLC at alpha or at beta. For the local Lipschitz continuity, I need more. I need the Petrov condition to be satisfied. Also, if I wanted to be locally Lipschitz in all the domains, so I will have to take the Petrov condition to be satisfied for all the points alpha and alpha. Okay, so now I'm ready to present also two regularity results that were before in the literature. But we have to pay attention that for these results, we have to add some assumption on F, which is F is linear. The multifunction F is linear. A multifunction is said it's linear if it admits the following representation. So now, in a linear setting, if I take that the Petrov condition is satisfied, I can deduce that T dot dot is going to be semi-convex near alpha beta. Also, in a linear setting, if I take F and minus F to be STLC near alpha or beta, this would give me that the epigraph is phi 0 convex near alpha beta. Now, the idea is control theory is used a lot in engineering, in economics, and medicine. And for all these real life problems, the multifunction F is never linear. So in real life, we are never working with a linear multifunction. This is the problem. This is what motivated the work in this paper. The idea, what happens, can we extend these two results if our multifunction F is not linear? And actually, the answer is positive. And before stating the result, I just want to mention that Nguyen in 2016 was able to develop a regularity result for the unilateral minimal time function in a nonlinear setting. So the difference is that he worked for the unilateral minimal time function, not for the bilateral minimal time function. So also another question, would we be able to extend Nguyen's result to actually to work with bilateral minimal time function? And the answer for both of these questions, positive. To do that, I'm going to also add some assumptions. So besides assumption F, which are the standing hypothesis, I want to assume that my upper Hamiltonian H satisfies these two conditions. So I'm going to call these hypothesis H. The reason why I need H is because one of the most important consequences of H is the Pontryagin maximum principle. So the Pontryagin maximum principle gives a necessary condition for the optimality of trajectory. And to be able to apply this theorem, we need these assumptions H. Now, also other than F and H, I need something else. I need the hypothesis R to be satisfied. So hypothesis R, what does it tell us? It tells us that there exists a certain delta positive such that the sublevel set of the bilateral minimal time function at the point alpha prime beta prime is actually phi 0 convex near alpha prime beta prime for all points in the neighborhood of alpha beta. So I'm going also to need this hypothesis. And now I'm done with the assumptions. I'm ready to state the result of the work. So if in a nonlinear setting, for a general multifunction, if I assume that R, this R, holds at the point alpha beta, if I assume that F and minus F are STLC near alpha or beta, this would give me that the phi 0 convexity of the epigraph near alpha beta. This is exactly proposition 2, which worked in the nonlinear setting. Now we have it also for the general setting. Now, if I take a weaker condition, which is the continuity near alpha beta, one can expect not to have the result, but actually we still have the result. The reason is because for the proof of this theorem, we only need the continuity near alpha beta. We don't need something strong as this. Okay, so a very natural corollary that comes from these two theorems is this one. So if I take stronger condition, if now the Petrov condition is satisfied, what can I tell about the bilateral minimum time function? So if we think about it, if we have the Petrov condition, so we have locally Lipschitz continuity. And also if we have the Petrov condition, we have continuity, so we have the phi 0 convexity of the epigraph. So now we have the phi 0 convexity of the epigraph with the local Lipschitz continuity, which gives us, by the remark, that T dot dot is actually going to be semi-convex near alpha beta. And this is also the generalization of proposition 1, which was done in the linear setting. So a very quick sketch of the proof. Basically, the proof we divided into 3 parts. In the first part, we derived some variational analysis. So Variational analysis, it's a combination between convex optimization and calculus of variation. So using this, we are able to connect the proximal normal cone to the level set with the proximal normal cone to the epigraph of the bilateral minimum time function. We use a lot of formulas that characterize the proximal and the horizontal subdifferential of the bilateral minimum time function on and outside the diagonal setting. After we're done with the variation analysis, we move to the sensitivity relations. So basically, sensitivity relations, it talks about how the output can be apportioned by the input. So we can derive some propagation result for the bilateral minimum time function along optimal trajectories. And in the last part, we prove the required inequality to prove the phi zero convexity of the epigraph. We use a very important lemma. The idea is instead of proving the inequality for all the points, we just prove it for the points of the form x f of x and y f of y, which limits the work a lot. Of course, we're going to use the Pontryagin maximum principle also in the proof. Those are some of the references used for this paper. And thank you so much for your attention.
Thank you a lot, then. Thank you a lot, Samara. And as usual, the floor is now open for questions, and you can unmute yourself and or raise your hand. Or both.
Can I ask a question?
Okay. Yes, please.
So, hi, Samara. So at the moment you mentioned the result where the key point for having some sort of semi-concavity, it was phi zero convexity of the epigraph, was the fact that balls were included in this multifunction, but you only required it at the points alpha and beta. So are you supposing that you already know that the value of this sort of distance function is finite, so that there exists a path to connect the points?
Do you mean in the main result?
It was an old result. No, it was not the. Sorry, but since I'm new to the subject, I still stick to the. It was a result by Noor, I think, one of the first that you mentioned.
This one?
Yeah, I think this one, the proposition one. Yes, exactly.
Okay.
So you get semi-convexity if zero is in the interior of the multifunction. So if a ball is included, but you only require that it is true either in beta or in alpha.
Yep. Yes.
So are you also supposing that this t is finite in alpha beta, so that there exists a curve?
Exactly, because we take alpha beta in the effective domain, so T alpha beta is finite.
Ah, okay. Okay. And from your assumption, if there are balls in alpha and beta, at least locally, there will be small balls.
Yeah.
Okay, I understand. Thank you.
All right. Is there some other question? Any further raise hand? Any remark? If not, I would thank once again Samara.
Thank you so much.
Thank you a lot. And I would already then give the screen sharing privileges to Samer.
Yes.
Just to see if, of course, I'm not actually in actual fact doing anything because I don't think I can be host. But please share. Let's see.
Can you see the screen?
I think it's working. Yes.
Okay. Perfect.
All right. Then I think in more or less 1 minute we could actually start.
Okay.
Sorry, maybe I shouldn't be so obsessive in keeping with the prescribed timeline. Can you try full screen? Does it show maybe slightly larger slides?
Okay, but I don't know how can
Or maybe you can even just zoom in a little bit. I don't know if it's still going to fit.
No,
no, maybe not so much. So there is not possible to do to make it full screen.
Maybe no. Okay, let me try.
You're seeing it with the browser. That's probably the problem.
Yes. Do you have it as a file? Actually, do you have it?
Yes. Okay, let me see.
Yeah, because you were sharing your screen and not an application. That's why, Samara.
Yeah.
So the PDF, I believe that we can start. So once again, I'm happy to introduce the talk of Samer Dweck, who's currently at the University of British Columbia, and he's going to talk about W1P bounds for the least gradient problem. So
yeah.
The floor is yours.
Okay, thank you, and thanks for the organizers for the invitation. So in this talk, I will show you how can we prove some, let's say, existence, uniqueness, and some regularity results on the solution of the least gradient problem using optimal transport. And so let me note that this work was in collaboration with my former supervisor, Filippo Sant'Ambrogio, and this is already published in Journal of Calculus of Variations and PDEs. Okay, so first let me introduce the least gradient problem. So assume you have a bounded domain omega and R2 with a given boundary data. So you have a BV function G on the boundary of omega. So this is given. And so the least gradient problem will be just the minimization of the total variation of the gradient of some BV function u over omega. And the only constraint here on this function u is that the trace of u on the boundary, it's exactly this function g. Okay, so here we are interested in proving existence of a solution for this least gradient problem, and then study the uniqueness, okay, if the solution u is unique or not, and trying to prove some W1P estimates, okay, on the solution. So the first very important point, which is already proved by Gorny, Ripka, and Sabra, is that this least gradient problem, it's completely equivalent to the following minimal flow formulation, okay, or this is the so-called the Beckman problem. So this is the minimization of the total mass of a vector measure W, okay, and let me assume here that W gives 0 mass to the boundary under the constraint that the divergence of W is 0 inside omega, and you have this Newman boundary condition where this measure F here, it's exactly the tangential derivative of this boundary data G, okay? In fact, it's very simple to see the equivalence between these two problems. Why? Because if you take any admissible function u in the least gradient problem, then just associate this vector measure W, which is the rotation of the gradient of u. So for sure, you have the divergence of W is 0 inside the domain omega, and it's clear that this Newman boundary condition will be also satisfied, okay? And moreover, it's clear that this vector measure W and the gradient of u, they have the same total mass. So this tells you that these two problems, they have the same minimal value. And moreover, so u will be a minimizer for the least gradient problem if and only if this corresponding vector measure, W, it's an optimal flow for the Beckman formulation, right? So, okay, in order to prove existence of a solution for the least gradient problem, so just you need to prove existence of an optimal flow W, this Beckman formulation. And if you prove that the Beckman problem has a unique optimal flow, so this implies directly, thanks to this one-to-one correspondence between minimizers for these two problems, this implies directly uniqueness in the least gradient problem. And in order to prove W1P estimates on the solution U in the least gradient problem, so just you need to prove LP estimates on the optimal flow W in this Beckman formulation. Okay, so that's why I say that these two problems are completely equivalent. Okay, so now if we consider, instead of the least gradient problem, let's consider now this Beckman formulation. And so my aim is to show you that this problem is also equivalent to some optimal transport problem. Okay, so first let's find a dual formulation for this Beckman problem. What is the constraint here in the Beckman problem? It's just the divergence of W, it's F, okay? Or in other words, I have this equality for all smooth function phi, okay? And so now I can rewrite the Beckman formulation in this way. So this is the minimization over all vector measures W, okay? And minimize the total mass of W plus now I replace this constraint on the divergence of W by this supremum. So this is the supremum over all functions phi of the integral of the gradient of phi dot W plus the integral of phi df. Why? Okay, this is very simple because if I take a vector measure W which satisfies this constraint, so okay, this term is always 0, and so the supremum is 0. Okay. Otherwise, so this means that there is at least a smooth function phi where this term is not 0. But okay, here I maximize over all smooth functions phi, so I can make this term large enough. Okay, I mean plus infinity, but as here we minimize over all vector measures, so we can forget this second case, and so this formulation is exactly the Beckman problem. Okay, and now if I can let's interchange the minimum and the supremum, okay, which is not true in general, but okay, let's interchange the minimum and the supremum, so we get the supremum over all functions phi of the integral. So here I have the integral of phi df plus the minimum over all vector measures W, okay, and here we minimize the total mass of W plus the integral of the gradient of phi dot W. Okay, now let's compute this term, okay, the minimum of this functional. So if you take a smooth function phi, which is 1 Lipschitz, then the minimum of this function will be exactly 0, right? Because if the modulus of the gradient of phi is always less or equal 1, so this term inside the minimum here, it's always non-negative, okay? So the best choice here is to take W equals 0, so the minimum is 0. Otherwise, again, you can make this term small enough, I mean minus infinity, but you maximize over all smooth functions. So at the end, you get that the dual of the Beckman problem, it's exactly this maximization problem. So this is the supremum over all 1 Lipschitz functions phi over omega, and you maximize this function, the integral of phi times df plus minus f minus. Okay, just here remark f plus and f minus are just the positive and the negative parts of f, which is, remember, f, it's the tangential derivative of the boundary data G, okay, in the least gradient problem. So these are two measures on the boundary of omega. Okay, but now, so remember again this duality result from the previous talk by Filippo, that this problem, it's exactly the dual of this Monge-Kantorovich problem. So this is the classical problem in optimal transport. It's the minimization over all non-negative measures, gamma over omega cross omega, and you assume that the first projection of gamma is f plus, the second one is f minus, and you minimize this transport cost, which is here given by the Euclidean distance, okay? So in other words, here f plus represents, for example, the mass on the boundary that you want to transport to the location, which is represented by f minus, but when you move a particle x, okay, to the destination y, you pay just the distance, okay, the Euclidean distance between x and y, okay? So in conclusion, we get these equalities, the minimum of the least gradient problem, the original problem in this talk, it's exactly the minimum of the Beckman problem, which is exactly the supremum of the dual problem, and this is exactly the minimum of the Kantorovich problem, okay? So now let's see how can we construct an optimal flow W for the Beckman problem using this Kantorovich problem, okay? So let's fix an optimal transport plan gamma for the Kantorovich problem. I mean, gamma, it's a minimizer for the Kantorovich problem, and let phi be a Kantorovich potential, okay? So I mean, gamma is a minimizer for this problem, and phi it's a maximizer for the dual problem, okay? And Okay, so now just from this duality, that the minimum of the Kantorovich problem, it's exactly the supremum of the dual problem. So we have this equality, the integral of the absolute value of x minus y d gamma, it's exactly the integral of phi times df plus minus f minus. But remember that the first projection of gamma is f plus, the second one is f minus. So this is exactly the same as the integral of phi x minus phi y d gamma. Okay, but the function phi, it's one Lipschitz. Okay, so this equality implies directly that phi x minus phi y, it's exactly the distance from x to y, and this holds for gamma almost every point xy. Okay, and so again, thanks to the fact that this Kantorovich potential phi is one Lipschitz, then you get that this function phi, it's in fact linear, right, on the line segment xy, and this is true for gamma almost every point xy. Okay, and so now from now on we call any line segment xy that satisfies this equality a transport ray. Okay, so in other words, this optimal transport plan gamma moves the mass along this line segments. Okay, I mean along these transport rays. And so again, thanks to this equality, so we can prove this differentiability result on the Kantorovich potential phi. So we can prove that phi is differentiable in the interior of any transport ray xy, and the gradient should be exactly the opposite of the unit vector of this transport ray xy. Okay. So now let's introduce this very important measure in optimal transport with Euclidean cost, and this is called the transport density. Okay, so for gamma, for the optimal transport plan gamma, I associated this transport density sigma gamma, which is defined as follows. So for any continuous function phi over omega, we define sigma gamma of phi as the integral over omega cross omega of the integral of phi on the transport ray xy times d gamma. Okay, what is the physical meaning of this transport density? So this represents the amount of transport, okay, taking place in each region of the domain omega. Okay, just from the definition. And now it's clear that, okay, this measure is well defined, but under the assumption that omega is convex. Otherwise, this is not well defined, okay? And moreover, if you assume that omega is strictly convex, then it's clear that this measure gives zero mass to the boundary. Okay, so this is just a remark. And now let's see how can we solve the Beckmann formulation using this transport density sigma gamma. So now let me define this vector measure W gamma. So this is exactly the vector version of this transport density sigma gamma. So this is minus the transport density sigma gamma times the gradient of the Kantorovich potential phi. Okay, and now we can prove that this vector measure W gamma is admissible in the Beckmann problem. So why? So let's take any smooth function phi and let's compute W gamma of the gradient of phi. So this is just the integral over omega cross omega of the integral between 0 and 1 of the gradient of phi times 1 minus tx plus ty dot y minus xy, because, okay, this comes directly from the definition of the transport density. And remember this result about the differentiability of the gradient of the Kantorovich potential. Okay, so I have this equality, but now let's just integrate this term here in time. So you get the integral of phi y minus phi x, but again, gamma, it's a transport plan between f plus and f minus. So you get finally that this is minus the integral on the boundary of the function phi times df, okay, which is exactly equivalent to say that the divergence of W gamma is 0 inside omega, and you have the corresponding boundary condition, okay, the Newman boundary condition on W gamma. And okay, so this tells you that W gamma is admissible in the Beckmann problem. Now let's see why this W gamma is in fact an optimal flow for this problem. The proof is very simple. Just compute the total mass of W gamma. Okay, so by definition, W gamma is minus sigma gamma times the gradient of phi, but phi is a one Lipschitz function, so the total mass of W gamma is less than the total mass of the transport density sigma gamma. Okay, but here, just in the definition of the transport density, when you replace phi by 1, you get exactly the minimum of the Kantorovich problem. Okay, but remember that the minimum of the Kantorovich problem, it's exactly the minimum of the Beckmann problem. So this implies directly that W gamma is an optimal flow for the Beckmann formulation. Okay, and for sure, W gamma here gives zero mass to the boundary if the domain omega is strictly convex. Okay, so yeah, this is a solution for the Beckmann problem, and thanks to the equivalence between the least gradient problem and the Beckmann formulation, so now we conclude that the least gradient problem has a solution if the domain omega is strictly convex. Okay, so this is about the existence of a solution for the least gradient problem. Now, let's see if the solution, let me call the solution U. So let's see if the solution U is unique or not. Okay, so again, let's come back to the Beckmann formulation. So okay, I say that this W gamma is a minimizer for the Beckmann formulation. Okay, but we can prove that any optimal flow W of the Beckmann problem is of this form. W, it's W gamma, or it's minus the transport density sigma gamma times the gradient of the Kantorovich potential phi for some optimal transport plan gamma. And here why I say for some optimal transport plan, because in general, the Kantorovich problem may have different solutions. Okay, so a priori, this property tells you that a priori the Beckmann formulation may have different solutions. Okay, but this is not true under some regularity assumptions on F plus or F minus. So this is already proved by Feldman and McCann. So if at least one between the measures F plus or F minus is absolutely continuous with respect to the Lebesgue measure, then you can prove that the transport density sigma gamma between them is unique, which means that sigma gamma in this case does not depend on the choice of the optimal transport plan gamma. And so this tells you that the solution of the Beckmann problem is unique. Okay, and so for the least gradient problem. Okay, and moreover, you can also study the LP summability of the transport density. So for example, De Pascale, Pratelli, Evans, and Sant'Ambrogio, they have also proved this result about the LP summability of the transport density. So if F plus and F minus are two LP densities on this set omega, then the transport density between them should be LP, and this is true for any P. But what is the problem here in this talk? The problem is that we cannot use these two results. Why? Because so F plus and F minus are two singular measures. Okay, so remember F plus and F minus are the positive and the negative parts of F, which is the tangential derivative of the boundary data G. Okay, so they are two measures on the boundary of omega. So we don't know, for instance, if the transport density sigma is unique or not. And we cannot prove, we cannot use this result to obtain LP estimates on this transport density. Okay, so, but anyway, I have already studied these questions with Filippo, and sorry, I don't have time to show you some proofs, but okay, let me just show you the results. So the first one is about the uniqueness of the transport density. So if you assume that omega is strictly convex, and if you assume that the source measure F plus is no atomic, which means that if F plus gives zero mass to any point on the boundary, then you can prove in this case that there is a unique optimal transport plan gamma between F plus and F minus. Okay, and so you have uniqueness of the transport density, and we can also prove some LP estimates on the transport density. So if we assume that the domain omega is uniformly convex, which means that the curvature of the boundary of omega is bounded from below by some positive constant, then if you have two, let's say two densities, F plus and F minus, two LP densities, F plus and F minus on the boundary of omega, and assume that P is small, I mean P less or equal to, then in this case you can prove that the transport density is an LP over omega. And in order to get some LP estimates for large P, so you need to assume more regularity on F plus and F minus. So for instance, if you have two Eulerian functions or densities, F plus and F minus on the boundary, bounded, then you can prove that sigma is in some space LP for p greater than 2. Okay, just for more details, so you can find, I mean, more details about the proofs of this results in this paper. LP bounds for boundary to boundary transport densities and W1P bounds for the BV least significant problem in 2D. Okay, so finally, just in order or in terms of existence, uniqueness, and regularity on the solution of the least gradient problem. So we get the following results. The first one about the existence. So if the domain omega is strictly convex and if the boundary data G is BV, then this least gradient problem has a solution. Okay. The second one about the uniqueness. So assume, moreover, that this boundary data is continuous, then in this case, the solution of the least gradient problem is unique. Why? Because the continuity of the boundary data in this case implies that the measure f, which is the tangential derivative of G, is no atomic, and then the solution of the Beckmann problem is unique, and thanks to the equivalence between the least gradient problem and the Beckmann problem. So this tells you that the solution of the least gradient problem is unique as well. And finally, about the W1P regularity of this solution U. So if the domain omega is uniformly convex, and if the boundary data G is W1P with P less than 2, then you get that the solution U for the least gradient problem is W1P. And in order to get again W1P regularity for large P, so you need to assume that G is C1 alpha. And finally, if the boundary data is C11, then you can prove that U is Lipschitz. Okay, so let me stop here and thank you so much.
Okay, thank you, Samer. I'm sorry we were going slightly beyond the schedule, but we were counting the minutes that were lost for the technical issues in the very beginning. So once again, the floor is open for questions. Please, you can raise your hands or unmute yourself.
Hi, Samer. It's Ahmed. It's good to see you again. Thank you. Thank you for the talk. So this result, so this equivalence that was proved in 2 dimension, then we get this result in 2 dimension, but can you at least generalize the problem? I mean, do you have the same result for the mass transport problem in higher dimension?
Okay, the problem is that it's not clear in higher dimension if we can prove equivalence between the least gradient problem and the Beckmann formulation. At least because, okay, here it's clear that we use this the rotation, I mean, of the gradient of U, but if we are in higher dimension, I don't know how can we prove equivalence, and maybe it's not true, I don't know.
But maybe just the Beckmann problem in higher dimension.
Oh yeah, yeah, and in higher dimension for sure, yes. So we can we have LP estimates for the optimal flow in higher dimension. This is okay, but the only problem or the only issue in higher dimension is just to prove equivalence between these 2 problems. Okay, but as soon as we have equivalence, I can prove directly the existence, uniqueness, or W1P estimates on the solution U for the least gradient problem. This is completely possible.
And I guess you proved this also for general anisotropic case, yes?
Yeah, sure. So if you replace, exactly. So here, I mean, if you replace this by the integral of phi of the gradient of U, and if you assume that this function phi, it's strictly convex, so you can prove the same results. And if you want more, now I'm working with Washtek, Barney, on the weighted BV least gradient problem. So in the case when you multiply the gradient of U by some weight K. So, okay, this is much more difficult because in this case you can prove that the weighted least gradient problem is equivalent to the transport problem, but with geodesic distance. And it's much more complicated to prove LP estimates the transport density in this case.
Okay.
Yeah.
Thank you, sir.
Yeah, thanks.
Okay, any other comment or question? If not, I will thank again Samer. Thank you very much for the talk. And thanks to, so we are finishing the session right here. And so thanks, and so also for, we are finishing the day. Thank for everybody for attending and the speakers for giving the talks. And we are resuming tomorrow at the same time at 10 a.m. Beirut time.